Hello, welcome to Converging Dialogues. This is Xavier Bonilla. On this episode, I am very happy to have on the podcast Henry G. Henry is a paleontologist. He's the senior editor at Nature, and he's written several books, including In Search of Deep Time, Accidental Species, and his latest, which we talk about, entitled A Very Short History of Life on Earth, 4.6 billion years in 12 pithy chapters. Henry is a wonderful man. He is a wonderful human being and quite brilliant. And so we talk about many things. We really cover, even though the book is quite small, we cover so much of what's in the book. And for me, this conversation really does a nice job, I think, of covering, the history of the Earth. I mean, as much as you can. We skip over some parts, but we really try and just kind of march listeners through, a history of the planet, and hopefully that comes through. We start by talking about some of his background and how he came to write his latest book. We go all the way back to the beginning. And we talk about the Big Bang and the very beginning origins of the Earth, as much as we know. We talk about how the sun and planets formed in our solar system. We talk about the importance of gravity, early life starting in the oceans, transition from unicellular to multicellular organisms. We talk about sponges, Rodinia. We talk about the Cambrian explosion. We talk about how we got to fish and vertebrates. We talk about the movement from water to land. We talk about tetrapods, talk about how plants began on the Earth. We talk about the importance of the Triassic and the Jurassic period. We talk about the unique features in the anatomy of large dinosaurs. We talk about the origins of mammals in the late Triassic. We talk about the importance of Homo Erectus, different species of humans living at the same time, the future of the Earth, and we have a little bit of a fun bit at the end, talking about science fiction and fantasy, of which both him and I are big fans of. I have to say, I've been a huge fan of Henry's work for many years. And so it really was an honor, a big privilege to talk to him for over 3 hours. He was just as excited as I was to have a long chat. And anyone that has been listening to the podcast for some time now knows I greatly enjoy long conversations, and he does too. So when we getting together, I said, look, we'll go as long as we can. He said, let's do it. And so I'm really happy we did that, because the history of the Earth is long. And I wanted people to kind of walk away with listening to the conversation saying, yeah, I have a really good thumbnail sketch of the history of our home, the history of our planet. And I wanted to talk about his book, which is fabulous, but I also wanted to talk a little bit about some more fun topics as well. And so we have the end part there talking about Lord of the Rings and Game of Thrones and sci-fi and fantasy in general. And I think that's nice to have in there as well, to keep it pretty lighthearted too. Sometimes, it's not just about facts and data, but Henry has a really big personality in all the best ways, and he loves this stuff, and he's just such a pleasure to talk to, and such a brilliant mind. And so now I bring you Henry G. I am here with the one and only Henry G. Henry, thank you so much for coming on. It's a big honor, big privilege. I'm super excited to talk to you.
So am I. Thank you very much for inviting me. This is going to be fun.
Yes, it absolutely will be. So tell folks that don't know who you are and what you do and what you write about and what your research is on, all that good stuff.
Yeah, I'm a recovering paleontologist. So I fell out of research after graduate school and fell in by a long series of entirely unlikely events as a junior news reporter on the international science journal Nature. I joined in 1987 on a 3-month contract. It's the longest 3-month contract that anyone has ever had. So I've been there nearly 34 years, but don't tell anybody. It's our little secret. And so after doing a lot of, I was hired as a news writer, wrote about everything. And I wrote a lot for the New York Times syndication service. So after having been a recovering paleontologist, I had to write about absolutely everything from AIDS to exploding galaxies. You know, like a news journalist has to write something authoritative by lunchtime on something they know nothing about. Right. So I became quite good at that. And but in a fairly short time, I asked to go and join the elite at Nature. They're the editors, you know, in the back room who actually select from the fire hose of original scientific reports that gets blasted on them, those few drops that will actually get published in Nature. And they were very keen at the time because nobody liked paleontology in them. They would only do it for they would only do it on sufferance. So they were very, very pleased to have somebody to throw bones at. So I started at that, and in course of time, I've taken on the evolutionary biology portfolio at Nature, and that's what I do now. I spend my day. It's the best job in the world. People send their best work to Nature, and I get to see it before anyone else does. And I learn about all kinds of amazing things, not just in paleontology. There's another thing I get to do is I get to cover the work of my colleagues when they're away. So I learn all sorts of neurobiology and molecular biology and all kinds of great stuff.
Yeah, that's the dream job right there.
I wish I could do astronomy as well as paleontology. Then I could be the long, long ago and far, far away editor.
There you go.
But sadly, no. I want to do all of it. All of it. Give it to me. It's mine. So I've been doing this for nearly 30-something years, and while I've been doing that, I've been writing books because you've talked to writers. You realise that you don't write a book because you feel like it. You write a book because you have to. So when I finished my PhD thesis, I started writing books on various aspects of evolutionary biology. And every time I finish a book, I swear I'm not going to write another book. And my wife looks at me with a knowing smile. And of course, within a few months, I'm writing another book. And I've done that ever since I finished my doctorate thesis, because I always have to be doing something. And the latest one, which you've invited me on to chat about, is called A Very Short History of Life on Earth. The very's got brackets on it, so it's a very short history of life on Earth, to use a Victor Borger spoken punctuation. And it does exactly what it says on the tin. It's a very short history of life on Earth. Although it actually looks quite like a fat book for a short history of life on Earth, I thought, hey, come on, if the world kept a week on a page diary, it would be 200 billion pages thick, and the book would be 9,000 miles thick. So I thought it is actually quite brief. But of course, most of those pages on its week per page diary would be really boring. So I've just done, it will be, after thousands of pages, small earthquake in Gondwana land, and then more thousands of pages. So I've cut down to the edited highlights.
Yeah. Well, look, I mean, that's the impetus for getting you on here, which is awesome. Look, the book is fantastic. If I wanted to give somebody literally the go-to distilled history of the Earth, this would be it. So yeah, as you said, the book is called A Very Short History of Life on Earth, 4.6 billion years in 12 pithy chapters. It's really good. It's really, really good. You could fit it in a handbag. I mean, it's really small in that way in terms of the size. And yeah, I mean, I don't know how you did this. I mean, you distilled so much information in each chapter, and yet it's extremely readable. It doesn't feel too dense or boring. And you really get, because one of the things that I've learned about talking to people is that everyone's kind of got an angle, right? Someone's talking about bipedalism, someone's talking about tropical forests, someone's talking about plagues, somebody's talking about and they all go through the history of the Earth, and they're just focusing on that one thing about through time on Earth. But you just get all of it. You talk about different animals, you talk about different climates, different environments. So it really is really just very masterful. It really is.
Well, thank you. I mean, I can tell you how it all got started.
Yeah, please.
You see, it all looks terribly simple. You just sit down and write a story of life on Earth. But of course, it was more complicated than that. I mean, back in my mind, when I was walking the dogs in the woods, thinking about what I was going to do, I thought, would it be nice to write a little history of life? Henry's History of Life, a nice little book, just to amuse myself. And then, of course, I completely forgot about it, which is what I usually do. Mm-hmm. And then at Nature, in those great days in the past when we used to go to an office, remember those? We used to go to these things. We used to actually get up and get on a train and go to something called an office. And I used to go and interrupt my good friend David Adam, who was our news writer and leader writer. And you'd like David, he wrote 2 very good books on, psychology. One was called The Man Who Couldn't Stop, about obsessive compulsive disorder. And it was a very personal view because I didn't know he's been plagued by OCD. And then he wrote another book called The Genius Within, about mind hacks and drugs to make you do better at exams. And he tries various ones out. So we used to get together and talk about the books we're writing. And I just finished a rather terse textbook, which was my kind of contractual obligation book. And David asked me what I was writing on, and I said, I'm not going to write another expletive deleted book. And he said, ignoring this, he said, why don't you write a book about all those amazing fossils that you've written, that you've handled, that have passed across your desk while you've been at Nature? And I thought, because there have been quite a few really cool stuff. I mean, I was there in the room where it happened when feathered dinosaurs were announced. I was there when the peculiar hobbit creature Homo floresiensis walked into the office, and all sorts of amazing fossils right through the history of life. So I decided to write a book, but it wasn't going to be just a history of life. It was going to be a kind of memoir. It was called Let's Talk About Rex, a personal history of life on Earth. So I talked about the fossils, but also I talked about the people, the people I'd met and the travels I've been on to meet them and all the fun I've had and the kind of background to each one of the researchers. And I told my agent, Jill has represented me since we were both young girls back in the last century. She was very keen to see the book, but I said, no, as I'm actually mentioning real people, I want to finish the whole book and send it to all the people and clear it with them. So she said, fine. So I sent it to all the people. They said it was great. And then I sent it to my parents. Oh dear. They said, now it's all very nice, dear, they said, but who apart from the people mentioned will really care? They said. So Jill was my agent, was more tactful than I, but then we worked it in and pruned it and reworked it and redid it until it eventually became the simple story that it should have been right at the beginning, which was I start at the beginning, I say once upon a time, and I just tell the story right through the end. Actually, it's beyond the end. Although it's 4.6 billion, I give you a 3 billion as well. There's another billion at the end.
That's true. Yeah.
So that's how it began. I mean, it's you've talked to loads of writers, and it's weird the way books happen.
It really is. Just from the beginning to during the edit process to, just to the end, down to, the different covers that, go out in the UK and the US. It's just all really, really, really interesting. I've always had an appreciation for writers. Obviously it's very, very difficult to do, but really just the process of publication and stuff is quite a labyrinth. So I think
especially at the moment with COVID. So it's a strange new world. Things keep being moved around for odd reasons.
So we'll just jump right into it. And so I kind of want to take as much time as you want, but to really talk about, the book, but really just tell the story of Earth. And when I was thinking about our conversation, I was like, well, if someone could, listen back to the conversation we have, could they have a really good snapshot of the history of, it's not just our planet, right? It's not just our home. It's many creatures' home, but it definitely is our home. It's the only place we know, and so obviously it's our home, and I think it's nice to know kind of the annals of our home. So in the beginning, right? You go all the way back, right? In the beginning, there was the Big Bang, right?
Yeah, there was the Big Bang at the beginning.
And how do we? So I I've read about this. I've read books on this, and in your mind, how do we come to know this? We'll ignore some of the kind of natural theological conversations about the origins of the Earth and universe, but how do we come to know about the Big Bang? And do people still push back about that's kind of the origins of the Earth, or how do we understand now what that is and how we get to the universe expanding?
Well, the origin of the Big Bang, the origin of the Earth, well, that goes back to astronomers looking out at what were called nebulae. Now, it was thought that all of the stars and galaxies we see were just one big mass. In between all the stars, there were these little fuzzy patches called nebulae. And then as people got better, they realized that nebulae were actually other galaxies. They weren't just little clouds close by. They were enormous clusters of stars a very, very long way away. And then it came to Hubble. Edwin Hubble said, hang about, all these galaxies seem to be speeding away from us. And the faster they go, the further away they are. And people had all sorts of ideas about this. One of the favorite ones was that of Sir Fred Hoyle was that matter was constantly being created in all the spaces between. It would just pop into existence, and that's why everything had to move out to make space for it. But there doesn't seem to be any evidence for that. What seems to be the case, and of course there's still enormous questions about it, is that if you see all the galaxies speeding away from each other, and you extrapolate backwards, obviously means they were closer and closer to each other. And at some point in time, everything originated from some little burp and followed by of infinite density, and everything expanded rather rapidly from that. The term Big Bang was given by Fred Hoyle as a kind of pejorative. He said, I don't believe it all happens in some Big Bang. So of course, the proponents of the Big Bang kind of owned this as their badge of ragged glory. But the kind of proof of it was that was the discovery of all over the sky, there are these microwaves, very, very, very long wave radio wave emissions that are the shifted back radiation of the very, very hot fireball at the beginning of the universe. And it comes from all over the sky at once. And there are tiny little variations in them that suggest how things became to clump. So that happened, 20 years ago or so, that, it was the afterglow of creation and all that. That seems to be the major evidence that the Big Bang happened in just the way it thought. Of course, the actual moment of the Big Bang is very difficult because the physics of what happens inside something of infinite mass and density completely fly out the window. Nobody has any idea. Of course, there's still a great deal of fuss about exactly when the Big Bang happened, because that depends on accurate measurements of how fast these galaxies are moving, and for that you have to have a good estimate of the distance to them, which is very hard to do. You have to do it by various kludges, like looking at the stars of different brightness and blah blah blah. It's not something I know much about, but the consensus is that it happened about 13-ish billion years ago. And what's exciting about it is quite soon the matter in the universe became clumpy. It wasn't universally distributed in a smooth wash. It was very slight variations in the density of the matter. And all you need is a tiny amount of variation for gravity to do its thing and clump and accentuate those differences. So matter got clumped together in some places and leaving other places in empty space. And so now we get to the bit where I start the book, where early stars were forming, and stars are they're dynamic entities. They exist by two forces in opposition. One is gravity trying to crush them down, because stars are very massive. The gravity is trying to pull everything in, and at the center they have these nuclear fusion furnaces producing energy that is forcing everything outwards. So stars live in this kind of equilibrium, and stars age because they eventually burn up all the hydrogen in their core, and then they run out of hydrogen, so then they burn helium and make other elements. And of course, that doesn't produce as much energy as producing hydrogen. So they're having more and more of a problem with gravity. And then they start burning carbon and old boots and rusty bedsteads and old furniture and anything they can find, until eventually they run out and the gravity goes woof and crushes a star, like in an instant. I mean, spectacularly in an instant. But then what happens is there's a kind of rebound. The star, because of all this stuff's been crushed together, it creates an even bigger explosion, and that's the supernova. The supernova is an explosion so big that it produces the equivalent of the entire millions of years of stars' radiation in an instant, and it lights up the whole universe. In fact, the characteristics of supernovae in distant galaxies have been used to measure the expansion of the universe, because they're in some of the distant galaxies, they're almost the only things you can see is supernovae. Of course, we wouldn't want one to happen too close to us, because the radiation would wipe out all life for light years around. Our sun is not going to be a supernova. It's too small. It has to be a giant star. And what happens in the supernova is all the other elements are created by lots of amazing fusion reactions. It was actually Fred Hoyle who worked that out.
And this
I'm sorry about the pinging noises.
No, you're good. This is how our sun came to be, right? There's this death of an old star, and then out of that comes this creation of a new star, which is our sun in our solar system. And,
that's right.
And this is happening. Is it easy to say in interstellar space that this happens for our sun that we rotate around, and for our planets in our solar system, and that this is likely to be happening in other galaxies and systems as well, that there are suns,
yes, of course.
And this is also happening as well.
I mean, what happens that the supernova produces a gravitational shock wave, and it's like a pressure wave that goes through. Think of it as a kind of giant sound wave, although it's not sound, but it has the same thing. And what it does is it passes through any gas and dust and ice and other refuse hanging around, and compresses it and rarefies it and compresses it into little into clumps. And of course, as we've seen, once you get something compressed into clumps, it compresses itself more, and then it starts to rotate like water going around your bath plug, and the center bit gets more compressed, and it gets so compressed that the fusion reactor lights up. And that's our sun. And you can see this happening even now in our galaxy. There are star-forming regions which are full of gas and dust, where stars are coalescing. And now it's possible to look at solar systems forming. There are young stars surrounded by disks rotating around them, like a panneau raisin Danish. Oh yeah, I think of everything in terms of food, man. It's terrible. So, but they rotate. If you can imagine a panneau raisin rotating, that's what they're doing, and and these little planets are coalescing into a system of planets as well. And this is happening all the time. It's just the circle of life in the universe.
It's just the rhythm of the galaxies.
That's how it happens. And 4.6-ish billion years ago, that's what happened in our solar system. It's the sun formed, and about the same time all the other planets did, although there were probably more planets and some of them were in different places. It took a long time for them, well, actually not such a long time, a few 100 million years for them to get into the right place. I mean, Jupiter, the big planet, might have originated nearer the sun and moved out, and some of the other planets moved in, and there were lots of other planets that walloped into each other, and eventually, after the great fuss, flapdoodle, and brouhaha, our solar system settled down into kind of the way we see it today.
But it's because of gravity that's pulling from all of that. That's where in these kind of clusters, if you will, that's what begins to, at a certain point, not always, but it will become the kind of core of a planet potentially.
Yeah.
And then the planet forms outside of that, essentially. But gravity is key.
Gravity is the thing that makes everything happen on these large scales. Gravity pulls matter in to form a star. Gravity clumps matter rotating around the star to become the planets. Now, some of these planets could have been stars. I mean, Jupiter is so huge. I mean, you could get 300 Earths into Jupiter. And it's got such gravity that it retains most of its atmosphere. That's why it's called a gas giant. Some of the smaller planets, like the Earth, have lost a lot of the atmosphere because they don't have the gravity to keep some of the more lively gases, like hydrogen, gravitationally attracted. But Jupiter is probably so hot that it could have been a star. I mean, Jupiter actually produces more radiation itself than it gets from the sun. So if it were any bigger, it would have started to shine as a star. But a lot of the other but all the other planets, they also had their gravitational attraction. Now, a planet isn't just a jumble of rocks. What happens is the gravity gets it to layer out like a layer cake, with all the dense bits going to the bottom, going to the middle. So in the crust, the Earth's crust, is the light froth of rocks. Aluminum, silicon, oxygen, aluminum silicates. They're very light, and they float on the top of a kind of squishy molten magma layer, the mantle, which is denser, and at the center is the Earth's core, is a rotating ball of liquid metal, incredible, and of nickel and iron, but also heavy radioactive elements formed in the final moments of the supernova. And because they're heavy, they go to the Earth's core. And the radioactive decay, the heat of that radioactive decay, is powering the forces of plate tectonics on the Earth. It's powering the movement of rocks we see at the surface. Ultimately, all these earthquakes and volcanoes and continental drift, the backdrop of life on Earth, they're powered by the radioactivity of uranium and thorium and other radioactive elements at the Earth's core that were left over from the explosion of the supernova so long ago. So we're all linked by link to this unimaginable disaster that happened billions of years ago. And if it weren't for that, we wouldn't be here talking now, which is, I'm very glad I'm sitting down while I've said that.
I'll say, we can understand this in terms of the universe and many galaxies, and then for ours and our solar system, and then other planets. So you were mentioning Jupiter, which is still a marvel and a fascination for many, scientists, obviously. In terms of the Earth, the Earth was, you say in the book that it starts out as this ball of fire, and then we get to water, right? And so maybe just briefly share, you can kind of give the timeline of how long, how many, billions of years that took, but how did that get from, okay, so we have gravity pulling, it gets to the core, we have this radioactive core, and then is it just a cooling down? And then how did we finally get to water to where we're at now?
Yeah, it just was a cooling process. I mean, back in the day is what geologists call the era of heavy bombardment. The Earth was trying very hard to cool down, but it kept getting interrupted because other planets kept walloping into it and basically stripping off the entire crust. And everything had to resettle again, and so everything was unsettled. It was molten hot. It was red hot. It was an ocean. If you imagine, those pictures of those incredible volcanoes in Hawaii, like Kilauea, it looked a bit like that over the whole planet. And the atmosphere was a thick fog. It had a lot of water vapor in it. It had hydrogen, but the hydrogen mostly boiled off, and it had methane and other unpleasant things in it. Nobody's entirely sure of the exact constitution, but it did have a lot of water vapor in it that was kind of gashed out of these molten rocks as they jostled around with each other. But eventually things settled down, and large bodies stopped walloping into each other very often.
So does that mean so early on in our history, as the Earth is forming, and as we're having our planet, are we just an amalgamation of other potential planets or asteroids or other things from space?
Yeah, this is a good point, because when people are trying to find out what the early solar system was like, they look at distant asteroids and comets and look at the constitution of these metals and the carbon compounds and things you find. So the Earth was very much what's called a kind of pristine primordial body. It hadn't evolved in any way. There hadn't been much chemical transformation. But it was settling down into layers, and the surface was constantly being stirred up. But then after a while, it cooled down. It took a few million years to do this. I mean, I'm really not quite sure, but it was back in the earliest days, Old Testament Earth. It was so the time is somewhat elastic. I mean, it was such huge, amazing apocalyptic events. It cooled down enough for all that water vapor in the atmosphere to condense into clouds and fall as rain. Now, just before that happened, a body hit the Earth, and a glancing blow, and shaved a huge bunch of the Earth off, and that condensed into the moon. So for a while after that event, the Earth had rings like Saturn. I don't know how long it would have had rings like Saturn, but that condensed into the moon, and we know this because the moon is actually a very big satellite for a planet as small as the Earth. It's rather special. And we know from moon rock that the Earth and the moon have very similar chemical compositions, which is unusual because a lot of moons are just captured asteroids that come in from somewhere else. So the Earth and the moon are a special pairing. And then after that, the atmosphere cooled down and it rained. And it rained and it rained and it rained. And never in his whole life, and he was 3 or maybe 4, had Piglet seen so much rain. And it was mostly from the atmosphere, but there were also comets, which are made of ice, walloping in every now and then to provide some more. And then it became a world completely covered in water. It was a world like that peculiar Kevin Costner film, Waterworld. Yes. Did you ever see Waterworld? Yes. I remember going to see that film with my wife, and those are the days BC. That's before children, and we went to see this film because we like Kevin Costner. We'd seen Dances with Wolves and Robin Hood, Prince of Thieves, and all that. So we saw this film, and my wife, who doesn't really say much unless she needs to, she was obviously really, really angry. I say, why are you so angry? And she said, if there was so much water in that film, why were they all so dirty? She said. So anyway, the world was a world of water. There was no land. And that had to happen when plate tectonics, all the fragments of the crust fragmented and forced apart and collided by the decay of the radioactive materials deep in the Earth, walloped together and produced land that was thrust up above the Earth. And land first started as little chains of volcanic islands like Hawaii, until you get loads and loads of these and they all slam together. and then you get the first continents. But back in the beginning, there wasn't a great deal of land. It was all sea.
Yeah. And that's what you can say that, even till this day, in current day, was it 70% of the Earth is still water, and it is of sorts. It's not a complete water planet, but for the most part, it is. And so it's interesting because the genesis of all of the Earth's formation and what we have as a planet is super fascinating. Before we start getting into life, I want to ask just a technical question. You don't have to go into great depth of it, but some people, I guess some skeptics, if you will, may say, okay, Henry, this is very nice. This is very good. But how do they know all of this? How are they figuring out stuff from 14 billion years ago or 4 billion years ago? How do we know all of this chronology of these things? What are the instruments? What are the ways in which we get this information?
Well, most of it at that age comes from radioactive decay. Radioactive materials decay, they emit radiation. And although each emission of radiation is random, statistically it builds up to something entirely predictable. A bit like when you throw a dice. You don't know what it's going to be at each time, but over a load of throws, you know that if the dice isn't loaded, you'll throw the same number of ones as you will of sixes. Yeah. So each particular kind of atom will decay at a certain rate. And because we know that rate, and we can look at the mineral, and we know how much material there probably was to start with, and we can see how much there was now, people can come up with a pretty good estimate, and it agrees with other estimates from other evidence of how long ago things happened. Now, back in the earliest days of the Earth, there are some really, really resilient minerals called zircons. They're little crystals of zircon. And people can do amazing things with tiny, tiny, tiny microscopic crystals of minerals. They can see how they've been shocked by other forces. They can look at the mineral composition and tell whether it's been recycled through the mantle, or it's been a part of a crust, or maybe it was a crust and recycled through the mantle and come back again, or maybe it's been they can tell the history, and because of the radioactive inclusions, they can see how old it is. Now, one of the most fascinating rocks in the whole of the history of the Earth is a tiny crystal of zircon, which has been dated at 4.1 billion years ago by radioactive decay. And inside is a tiny puddle of carbon graphite.
Wow.
Now, inside that tiny puddle of carbon graphite, the carbon atoms are in such a state that you can tell there might have been a ghost of a shadow of an after image of life that life was on the Earth 4.1 billion years ago. And this comes from another clever thing. You know, atoms have all sorts of varieties called isotopes, and carbon has them. There's carbon-14, which is radiocarbon, that decays quite quickly. But then there's carbon-12, which is almost all carbon. And then there's carbon-13, which is in between. That's not radioactive, but it's quite rare. And life, as part of life's biochemical processes, tends to fractionate the carbon. So there's slightly more or slightly less, I've forgotten, carbon-13 compared with carbon-12 than you'd expect if there weren't life.
Wow.
Now, there's all sorts of arguments about this. This is all hedged with caveats.
Sure.
But there's a ghost of a chance that even when the Earth was still being bombarded with large comets and things, life was there. We don't know what kind of life it was, and we just know it from these tiny, tiny crystals. And that's the evidence is for the early life on Earth and the earliest days of the Earth, because almost all the rocks from that age have disappeared. They've been worn away. They've been recycled into the mantle. But some of them come back. We see some of these, as we were talking about earlier, these pristine rocks from the early solar system that haven't bashed into anything. This is why you have these spacecraft going to asteroids and scooping up bits and bringing them home, because they'll give clues about what the solar system was like while the planets were forming.
Yeah.
And so that'll give you a kind of baseline.
Yeah.
But that's really kind of the evidence. And a lot of it is circumstantial, a lot of it based on chains of reasoning, but each chain is pretty well established by other chains of reasoning. And it's marvelous. I mean, it's like a cliche. Science is a kind of detective work. It's like CSI. I mean, you don't see life in that little smudge of graphite, but it's a kind of trace where life might once have been. It's like the kind of breath left by a departing person in the room. So these are the evidences on which all these events are based.
No, that's really helpful. I think most people listening to that will really appreciate that. I mean, it's really quite spectacular to hear how that could be true, and then also how how we're able to find that. Which brings me to my next question is, how, well, we won't look in the kind of, again, the question that no one really has an answer to is, why life here as opposed to any other planet that we know, or even planets in other solar systems. But how life began on Earth seems curious, right? As we've been talking about, it arose out of kind of disaster. So the why is to me less interesting than the how, I guess you could say. So I guess one thing I do want to ask is, if the Earth's evolution was no different from other planets in one way, is it true to say that life could be on other planets as well, ostensibly?
Oh yeah, I reckon that life in some form is pretty much inevitable on a planet similar to the Earth. And this is, I say this because apart from its existence, life's existence is amazing.
Yes.
The next most amazing thing, or even more than that, is how quickly it happened after the Earth formed. Yeah. And while the Earth was still being bombarded by large asteroids, and it wasn't a very, you wouldn't say it was like Darwin's small little pond. It was really quite cataclysmic, the things that were going on. Now, in the book, I basically tell a story, and in the main part of the book, because I'm telling a story, I don't stop to give caveats or explain other people's points of view. All that's in the footnotes at the end. I really wanted to do it like a kind of Talmud, I'd have the main text in the middle with all people's commentaries around the side. But you can't do that these days. The printers don't like that. So you have to have them all at the back. And apart from the very end of the book, the bit where I talk about the origin of life is the part where I say this is closest to be what scientists call making stuff up, because nobody knows how life originated. Although there's some very, very clever ideas. And one of them is that life originated in the very deep sea, in these hydrothermal vents, which are places where they're in the deeps of the sea, there are cracks in the Earth's crust because of tectonic action, where jets of superheated water, I mean, it's still water, but it's like 300 degrees because the pressure is so great, are jetting up from the sea floor, and they're full of juicy minerals. They're full of rich in chemistry. They've got loads and loads of minerals in them. And there is... So that's one thing. And also, all these rocks you get that are formed by the condensation of all these minerals, these weird towers of condensed lava and something, they're all like pumice. They're all full of little holes. And one can quite easily imagine that mineral just gets deposited in these little holes because of turbulence. There's some parts that are less energetic than others. So things settle into the little channels off to one side and in the tiny microscopic holes. And because there's all sorts of organic material, it'd be quite easy to get some scummy membranes forming over the holes, or scummy little membranes. And as soon as you have membranes, you have life, because the one thing, I think the essential ingredient of life is something called the proton pump. What membranes always seem to do is find some way to pump protons which are basically hydrogen atoms, from one side to the other. They all seem to do this. All kinds of life seem to do this. And all you need to do is have a membrane separating one thing from another thing. And you get, what you do is you get a constitution different from the outside world. And the proton pump is creates energy. It produces energy to do work. There is a great guy in London called Nick Lane who works on the origin of life, and he did a book called The Vital Question, and that switched me on to the idea that it's these ideas you get membranes, and as soon as you get membranes, things are going to want to pass across them, because a membrane, even if it's leaky, it'll just by nature have some things that it'll separate things of different concentration. So you get a different kind of soup on one side of the membrane. You have minestrone on one side and cream of mushroom soup on the other side. Right. And because of just the laws of physics, things will want to diffuse through. And so there were proton pumps that made sure some things got through and not others. And because protons are electrically charged, that produced a voltage across the membrane. Now, it might be a very tiny microscopic thing, but in terms of the space, that was an incredible electrical potential. So life started by inventing a kind of battery. Batteries, it's like battery powered. And once that started to happen, life began to form by increasing complexity in little membrane-bound bubbles and budding off little bubbles that went to do their own thing. And eventually, by who knows what forces, they started to replicate. They started to have a heritage. They started to have a genetic heritage. Bubbles had a memory formed by DNA or RNA or something. Exactly what the earliest genetic material was, nobody really knows. But now this is just my view. I think the little membrane-bound bubbles happened before the genetics. And that kind of stabilized. When that happened, that stabilized and directed and organized and made more regular and predictable the generation of these first cells, is what they became. Now, of course, a lot of this is unbelievably speculative.
Sure. But it's interesting because it's many of these things are, no one's ever going to really know. Pinpoint, obviously so long ago. To me, the theme that I'm taking away from this is that the shortness of it. So if we roughly say 4.6 billion years, the Earth is there. From there, 4.6 to 3.6, that's where we have life. We're just talking about a billion years. And so
by 3.6, life was everywhere. It was well established.
Right. So what can we say roughly? I mean, people are going to debate this. We don't really know. But was the first living thing, I guess, if you could call it that, was it just the single cell stromatolites or is it something else?
Well, there were precursors. There was a long precursor to living cells. I mean, these days, what we call living cells usually have DNA or its friend and relation RNA as a kind of genetic material. And it would have been some bacterial-like cell. Yeah. About that, probably similar to pond scum. They're called blue-green, what we used to call blue-green algae, cyanobacteria, that are the simplest forms of life. And they are quite gregarious. They get together in long, hair-thin strands or in sheets, scummy sheets. And these are the blue-green scum you can still see today on ponds. Not the duckweed. I mean, it's the kind of looks like an oily iridescence almost. And what happened was they formed these colonial mats, and then they'd be washed over by sand, and then the algae would grow another mat on top, and then there'd be more sand. And so you'd get these layers of sand and sediment and they become these cushion-like mounds. And you still see them today in some places. In Western Australia, there's a bay full of all these mounds, these stromatolite mounds, and they still live there because the bay is too salty for anything else. Because stromatolites ruled the world for 3 billion years, but that was before anything evolved to graze them. But still there are what's called microbialites. I mean, in some places, some soda lakes. There's a place in Turkey, Lake Van, that has these microbial accretions that go up from the base. Usually in places where it's too acid or too alkaline or too salty for other things to tolerate. I mean, you get all this stuff in hot springs in Yellowstone and places like that. So these are kind of echoes of the earliest days of the Earth, these kind of aggregations of very simple but robust organisms, and they cover themselves they secreted all this slime that makes them slimy, but also help bind them together into membranes and sheaths. So these were the earliest and most long-lasting and successful forms of life on the Earth. And I wouldn't be surprised if on other planets there weren't things very similar. If there's anything more complicated, that's another story. But just, my two penneth, given that we only have a sample of one, I reckon that simple life is rather common in the universe. Because it just seems to happen almost inevitably. You get some little scummy membrane, and whoopee, you have some transport system and a way of gathering energy that just kind of happens.
Yeah, it's interesting. I'm not extremely well traveled, but I've been to a few places, and I've been to Iceland. I've been to the Galapagos Islands.
Oh, you've got two places I've never been. I'd love to go.
I've been to Yellowstone as well, and it's
I haven't been there either.
It's
more
interesting
well traveled than me.
Because when you get to those places, I remember when I was on both Iceland and Galapagos, it feels like you go back in time to like the beginning of the Earth. Like, cause it's just a volcanic island, and obviously it's evolved and stuff, but it just feels super ancient. Like it's not like it's like beyond civilization, beyond humans, beyond the mammals. It just feels like this has been here, through all the extinctions, et cetera, et cetera, et cetera. You just feel like, whoa, it's almost like you're transported in time to.
But the funny thing about all these places is they're all quite recent. They were made quite recently. And that basically shows that the Earth is continually renewing itself. And then when new land forms, inevitably, it's going to be like all the land that ever was formed. And back in the earliest days of the Earth, that was the kind of land that was formed. So you get this idea. I mean, Iceland is quite a recent thing. I mean, it's a magma plume on a spreading center. I mean, it's the most incredible. Hawaii is the same. I mean, you go to the Big Island and so on. I've never been. I've been to other places in Hawaii. And the Galapagos is a chain of volcanic islands. Well, when the first land formed, it started as chains of volcanic islands, all these things. And it's only when they started to be eroded and more things came up and they were glommed together that you started to have continents.
Yeah, I guess one thing before, because I want to ask you about Rodina, but I want to ask about first, how do we get sort of from the very early formations of life to unicellular organisms, and then eventually we get to multicellular, which is what we are, and fungi and all these things. How do we get from that process of one cell to multiple cells? And is that only because of CO2, or how do you see this?
Well, there are a number of things. The first is that bacteria are very chummy and gregarious, and they live in this kind of soup in which they're exchanging material, where you will never have one bacterium all on its own looking rather lonely. You'll have loads of them, all different ones living together. And although bacteria all look very similar, I mean, there are rod-shaped ones and there are circular ones and there are spiral ones. That's pretty much it. They all have wildly different chemistries. They're all doing different things. So the waste product of one can be a meal for the other. So there's a constant exchange of material in bacterial communities, and also an exchange of genetic material too. This is how you get resistant strains of bugs in hospitals. If a bacterium doesn't have a resistance gene to an antibiotic, it doesn't have to spend millions of years evolving one. It just picks one up in the kind of goblin market in which it lives. So what happens? The first thing is bacteria of different kinds are very gregarious. They like to live together. And eventually they took that group living to another level. There were bacteria that grouped themselves together in a common membrane, and different members of that community specialized in different things. Now, the latest view is that there was a kind of bacterium called an archaeon. Archaea are particular kinds of bacteria. They're very different from regular bacteria in all sorts of ways. But there was a tiny little archaeon that needed the help of methane metabolizing bacteria. And what it did was it lived in a community and grew little extensions to these other methane-loving bacteria, and they started exchanging material until eventually you get communities that are more than just freewheeling bacteria living together like housemates, that they could go away at different times. What happens is one of the housemates becomes the keeper of all the history, the rules, and all the other ones don't bother about that. They just specialize in different things. Like one of them specializes in generating energy. And this was a kind of bacterium, and they eventually became the mitochondria, which are these little power packs that you have in all cells. Yeah. And in plants, these green cyanobacteria became the chloroplasts, and these tiny green bodies you find in the leaves of plants. And there are other ones that do other things. So what happened is you've got these cells where the genetics was much more ordered and concentrated in the nucleus, which was the distant descendant of that archaeon in the middle. And it's basically what happens is you get this increasing complexity, but the payoff is improved efficiency. I mean, it's exactly like Adam Smith and The Wealth of Nations. If you have, Adam Smith at the beginning of the Industrial Revolution, he noticed that if you have a lot of artisans working in cottages trying to do all the steps of a process themselves, it's much less efficient than if you have a factory in one place where each worker is doing one step of the process. You produce more cheaply, more quickly of the product that you're producing. I mean, at the cost of the individuality of each member, the community as a whole can do more, be bigger, go further, attract more resources to itself. And these were the nucleated cells, and nobody knows quite when they arose, but the likelihood is they arose during a period called the Great Oxidation Event, which was this cataclysmic event in Earth's history that came across for reasons that nobody's quite sure about, when oxygen became much more common. And also there was a huge ice age. Now, it could have been because there was a great deal of tectonic uplift of new land. What happens whenever you get new land, carbon dioxide in the atmosphere gets sucked into the rocks and combines in it to make carbonate rocks. And once it's sucked into the rocks, it's no longer in the atmosphere. And you know what carbon dioxide does in the atmosphere? It causes the greenhouse effect. Right. So without the carbon dioxide, everything cools down. Now, back in those days, okay, there wasn't so much land to weather, but the sun was a lot cooler, a lot dimmer than it is now. So there was nothing to stop the Earth plunging into a deep freeze for 300 million years. So the Earth was frozen all over from pole to pole for 300 million years. And it's just this kind of apocalyptic disaster that prompts life to do things more efficiently. And in this case, by evolving bacterial communities that were so integrated, they became another order of organism, the nucleated cell. And that happened 2-ish billion years ago.
So this sounds just like many things we see today, even within our own body, even within other groups. There just seems to be at literally at the start of the Earth and in many things on the Earth, this evolution of cooperation. This is a very interesting, if you're telling the story of cooperation in many different facets of the Earth, that is literally the theme. To have life is to have cooperation. You almost can't separate it.
And it's a theme that came out as I was writing the book, because I didn't quite realize it. What seemed to occur to me was, as I was writing the book because I was deliberately taking this very big, broad brush scale, that when threatened with adversity, life invents a new form of cooperation.
Yeah.
So back in the Great Oxidation Event, they didn't die out. They just became more complex and formed a new kind of cell. Now, there are still loads of bacteria around. I mean, they're still the most common form of life, but they became the nucleated cell. And then the nucleated cells started to get together to form multicellular organisms. And that happened another billion years later.
She's someone that's been on here, and she's a friend, is Nicola Rehani. She wrote The Social Instinct, and she talks about the story of cooperation. She talks all the way at the gene level, how genes are cooperating together within our own bodies, and then talks about, kin selection and how it works with families, and then as we have interdependence, reciprocity, etc., and how we branch out for humans and then other organisms. And it just reminds me of it's just so powerful. But you mentioned this in the book, and you say it now, is it really is just incredible that part of the story of living things on the planet is a story of some form of cooperation, especially when there is some type of adversity or some type of disaster. There's some type of solution there, all the way down to the bits and parts of life, which is fascinating to me. I want to ask, because I haven't asked it yet. I like this kind of stuff. I'm such a systematic person in some ways. So up until this point, so we're getting to multicellular, cells, at least organisms, and then we're getting to the kind of the shaping of the Earth here. How do we what's the not taxonomy, but how do we describe the periods of the Earth from the very beginning? So like the first period of the Earth, how long, and what period are we up to now, I guess?
Right. Well, the earliest days of the Earth are called the Hadean, Hades, up to about 4 billion years old. And that's kind of stuff we know very little about. Sure. Because there are no rocks that age that are testament to those times, except, those, do you remember I was talking about these tiny zircons that are 4.1? These have basically been weathered out of earlier rocks that no longer exist. Wow. They're all that is left. So the Hadean, and then there was the Archean, the ancient eon, that goes up until about 2,500, 2.5 billion. Gosh, all these numbers. I have a friend who's an astrophysicist, or was an astrophysicist, but when she wasn't being an astrophysicist, she was an accountant. And she was an accountant for all these venture capital firms. And she says, how many noughts are there in trillions? She used to say. So we're talking about big numbers. So between 4 billion and 2.5 billion was the Archean. And that was the period from basically the Earth being stable enough to form life until about the Great Oxidation Event. So that was when life formed, when photosynthesis happened, until the Great Oxidation Event. Then between 2.5 and 0.5 was the Proterozoic. So that was when the early nucleated cells got together to produce living organisms. And they started to do this after about 1.8 billion. And there's a period between 1.8 billion and 0.8 billion, well, 800 million years ago, that geologists who need a certain amount of apocalypse in their life before they get out of bed call the boring billion. But it wasn't actually boring for the origin of life. It was when living organisms started to get together in forms that we reasonably recognize today through half-closed eyes. They were the earliest fungi. They were the earliest algae or seaweeds. And they were the earliest stirrings of what one might eventually call animals. And these slowly got themselves together before about 800 million years ago. And then, of course, massive disaster. And you hinted it too, the great supercontinent Rodinia started to break apart. So I can talk about that.
Tell us how the shape of this. So we're getting some organisms on the Earth, and then there's Rodinia. So tell us how it looked pretty different from Earth that we know today, but then how that kind of pushed us towards Earth.
If you looked at the Earth from space, it would have looked, roughly like it does today. It was a blue planet with clouds and looked rather pleasant. But if you look closer, you'd find there were fewer land masses and they were all in different places. So the lands move around. This is because of the continental drift. And there's a cycle to continental drift. The Earth breathes. It's a kind of 500 million year breath. So every so often, all the land masses in the world tend to get together, they glom together into a large land mass, and then they tend to rift apart, and then they do the same thing again, but maybe in the different places. And this is described in a marvelous book by a friend of mine called Ted Neild, who's a geologist, and he wrote it in a super book called Supercontinent. And he told me that this is not about pelvic floor exercises. It's about continental drift and about how the continents have been moving. Now, the great supercontinent that everyone's heard of is Pangaea, right, that was at its height about 250 million years ago. But there were supercontinents before that. The one before that was Rodinia, about 800, 750 million years. And before that, there were other ones, although because each one is overprinted with the other ones, they're harder and harder to establish.
Sure.
But there are some very, very old bits of rock in the world that are still at the cores of ancient continents that are still around in bits of Greenland, South Africa, the Canadian Shield, bits of Scandinavia, bits of Russia, bits of Western Australia in particular, which are the old, much beaten around hearts of really old continents that have never been sucked back. All their edges have been smashed around a bit, but it's just the nubbin of those continents. So some of these rocks go back to the earliest times, and some of the earliest evidence of fossils comes from fossils in Western Australia, the first reefs, and in Greenland, or, old reef communities. Anyway, so what happened was, at around 1 billion years ago, I mean, talking very broad brush, most of the Earth's continental land masses had got stuck together into this large supercontinent, which is called Rodinia. And that started to break apart. And what happened was, it broke apart in such a way that all the fragments were around the equator. And what happens in hot places is weathering happens really fast. You get torrential rains and storms, and there's heat, and so carbon dioxide was sucked out of the atmosphere by all these newly bits of rifted continent, and there was another ice age, or about 2 or 3, that lasted for 80 million years. Now, it wasn't as severe as the one that happened all those billions of years ago at the Great Oxidation Event, where the Earth was covered in ice for 300 million years. There were more, I mean, so why were the ice ages not so severe? I mean, only 80 million years the Earth was covered in snow, Although there was more land and more weathering, the sun was that much hotter. So the sun is slowly increasing in heat, and the carbon dioxide is slowly decreasing over the Earth because there's more land for it to be sucked into. And these two factors are critical in shaping life on Earth. So what happened? Rodinia broke up. There were these ice ages, and because of that, life made a step to another. It made a step change to increasing complexity, and that was animal life. That was a result of the that's what I posit. I mean, you get 2 paleontologists in a room, there'll be 3 or 4 opinions. But it does seem that was another time of adversity when life pulled up its socks and evolved into a new and more efficient forms that could do a lot more with less. Multicellular organisms, especially animals. And they came out of that period.
And this is where the sponges start to happen. So we're starting to look at sponges here.
Yeah, I mean, before I wrote this book, I wasn't really very much aware of sponges. I mean, I'd found them in rock pools, and they're very modest creatures. And something has happened. My book's not definitive. The great thing about it is it's already going out of date. So buy one quickly, people. We're all going out of date.
Yes.
there's been a lot of debate about sponges are the simplest animals, and they really are very simple. They're very modest creatures. They're made of gluey bunches of cells, and through which all sorts of these channels form, and the sponge sucks in water through waving little cilia on some of its cells, and it siphons out any of the old muck that just passes through, and it feeds on it. And that's all sponges do. And sponges have no organs, they have no tissues. If you break a sponge apart and put it back into water, it'll form again into another sponge. It'll be a different shape, but it'll be still as functional as a sponge. So they really make very few demands on life. And there's been a lot of debate about when sponges evolved. People have thought that they evolved about 850 million years ago, about the same time as Rodinia was kind of breaking up. But there hasn't been much concrete evidence. Well, now there is. A lady called Elizabeth Turner at Laurentian University in Canada has found evidence of sponges rather like bath sponges that lived back in those days. They lived attached to these microbial reef ecosystems. Now, a lot of this is still very controversial. People say that's not a sponge, that's something else, because interpreting these really old fossils is very, very hard.
I'm sure.
And of course, sponges don't look like anything in particular, so they're kind of strange textures in the rock that have survived after all these. So sponges, what they did, there wasn't much oxygen in the atmosphere. The Great Oxidation Event produced lots of puffs of oxygen into the atmosphere, and it settled down to about 2% of the atmosphere by volume was oxygen. Now, that was a lot more than there had been, where it was just a trace contaminant. But it's much less than it is now, which is 21%, and far too small for any animals larger than a dot to live on. But sponges can survive with very little oxygen because they don't move around. They sit in the same place, filtering gunk and just unwanted rubbish from the oceans. So what they did was they filtered out all the products of decay. They cleared up all the rubbish out of the oceans. Now this allowed the ocean to be oxygenated and provide and gave scope for more oxygen to happen. Because what happened was the Earth was stagnant. It had no oxygen in it except very near the surface and in the atmosphere. And the reason was the water column was full of decay bacteria, and they used oxygen, and so any oxygen that was there was sucked out immediately out of the water by decay bacteria. But when the sponges at the bottom filtering out all the products that the decay bacteria used, basically it cleared the water column all the way down to the bottom. So the water became clearer and had the potential to become more oxygenated. And this happened at about the same time as the invention of one of the great moments in evolution was the invention of the butthole.
Yeah, this part was super fascinating to me when I was reading this in the book, and it kind of snuck up on me. I'm reading the book, and then all of a sudden we're talking about the anus, and I said,
it was one of the great inventions of evolution, because
explain it to us. Wow us with the evolutionary story here.
Well, it's one of these modest things that actually has world-shattering consequences. So when next time you're sitting on the John, think about the great evolutionary heritage in which you're participating.
Certainly.
When animals were very small, in fact, when organisms were very small, they were so small that they could diffuse food in through their surfaces, and they could diffuse water, waste products, carbon dioxide, ammonia, whatever, out again. But once you get bigger than about a period at the end of a sentence, it's more efficient to have a particular place on the surface where things come in and out, a kind of space dock. And so if you look at fairly simple animals like jellyfish and simple worms, they have one place, it's the mouth. Right. And it's also the anus. So things go into the gut and are metabolized, and all the waste products come out, and they go in and out of the same place. Now, what happened was some animals evolved a different place for all the rubbish to come out again. So rather than having all the all the food coming in one place like a bag and going out of the mouth of the bag. All the food would go in the bag and be digested like a production line and keep going until all the waste came out at a separate hole at the other end, called the anus. And that made a through gut. And one thing that this did is that once you have an anus, it suggests that the waste products aren't just a diffuse wash. They're actually concentrated into pellets because waste production is much more efficient.
Yeah.
And once you had pellets that could actually sink in the water rather than just wash diffused out, all the feces sank to the bottom of the sea, and all the decay bacteria had to go to the bottom to chase after it. That was another thing. And of course, the sponges get to work on all this, recycling it all. So that was another thing that cleared the water column. So it was the invention of little animals with the anus that helped clear the water. It became more oxygenated and also allowed animals to get bigger, because animals with through guts, you can have a lot more gut in a smaller space.
Precursor of a digestive tract, essentially.
Exactly, that's exactly what it was. And they can get bigger, and so the animals got bigger, large enough for us to have been able to see them, and they had plenty of oxygenated water to play in, and then became then the evolution of animals was set to take off.
Yeah. So, I mean, this is absolutely fascinating, because then not only is there, an exit door, there's a kind of digestive tract that's being that's evolving. And so as this is happening with these creatures, we start to get to some of the Precambrian and then the Cambrian explosion of life, right? The Cambrian explosion is how you say it. And so what was as the Earth is evolving here, what was in the environment aside from calcium, that was essential for the development of life to occur? And there's a part in the book where you say that, by the end of the Cambrian period, all the major groups of animals still around today had made their first appearance in the fossil record, which is absolutely stunning considering all the extinction periods. So how do we understand what the environment was to get this like big Cambrian explosion of life?
The Cambrian explosion was terrific, and it was actually known to Darwin, and he was very puzzled because back in his day, there was loads of life in the Cambrian, trilobites that every rock hound has in the collection. Loads and loads of fossils are being found all the time. But before the Cambrian, absolutely nothing.
Yeah.
And Charles Darwin was rather puzzled by this, that there seemed to be a sudden jump in the origin of life, in the complexity of life. But and there's been a lot of debate about this over the years. People thought that maybe the base of the Cambrian wasn't a continuous deposition. Maybe there'd been some massive amount of erosion, and there was a whole period which we didn't know anything about that was disappeared, in which things would have evolved. That doesn't seem to have been true either. So things did appear. But what seems to have happened is yet another period of massive weathering. There were creatures just before the Cambrian, these beautiful, strange Ediacaran organisms that some were more animal-like, some were, who knows what they were like. They were colonial, very beautiful, delicate, frond-like organisms. But they were soft-bodied. So you only see kind of compressions of them. And there were things recognizable as flatworms and jellyfish and maybe precursors of mollusks and other things, but they're hard to recognize because there's no shells, there's no hard parts. But then another episode of weathering happened when basically all the there wasn't any soil as such, but all the rock, all the earth down to bedrock was washed into the sea over a short period at the beginning of the Cambrian. And this had two effects. One is, once you dump all that earth into the sea, it raises the sea level.
Sure.
So the sea is encroached on the land, and there was all of a sudden lots of shallow seas for things to live in. And once there's opportunities, things started to evolve massively. And the other thing was the sea was full of calcium, which, because all these animals were evolving massively, and you had all these animals with anuses and mouths at one end and anuses in the other, and an animal with a mouth at one end and an anus at the other is usually going in a particular direction. Mm-hmm. It's usually looking for something, and that's usually for some other animal to eat. Mm-hmm. And that's when the Garden of Eden, after the Ediacaran Eden, where everything was very beautiful, came to an end, animals started to eat each other. And so the response to that was to evolve armor plating. Mm-hmm. And the response to that was to evolve teeth. Mm-hmm. Now, the Ediacaran animals could have done, they might have done that, but I don't know what with. I mean, it was like the Big Rock Candy Mountain. All the bulldog's teeth were rubber. They had no hard minerals to do it with. Mm. So all of a sudden, at the base of the Cambrian, you see fossils with shells and teeth. Mm-hmm. And this happened because of this intense weathering event that happened at the beginning of the Cambrian. Mm. And so you get all these, I mean, the animals were kind of there, but it was because of this weathering that they were spurred into evolution. Mm. And it's true, in that period of 50 million years or so, all the major animal groups that we know now evolved. Mm. And everything since has been a kind of riff on the same themes. Mm-hmm. I can tell you a secret. It used to be all the animal groups that evolved except for bryozoa, the moss animals. Well, folks, I can tell you now, there's now fossil evidence for Cambrian bryozoa, so we've cleared that one up. But the Cambrian explosion wasn't so much a slow detonation. It was a kind of rumble that started with the breakup of Rodinia and set in a chain of events that didn't quite peter out until, well after the end of the Cambrian. Mm. So it was a whole, concatenation of events that allowed the increase in sea level, the infusion into the sea of loads of calcium that animals could use to make calcium carbonate bones and calcium phosphate armor and teeth and so on, and that fueled another great burst of evolution. So by the end of the Cambrian, the animals were the same kinds of animals we see today, although we might not have recognized them. They still looked a bit kind of weird and antique in some ways. There was still quite a lot of change to come, but now we've already covered 9/10 of the Earth's story. When we're back to we're now a mere 500 million years ago now.
Well, this is the really fascinating part about it, is that there seems to be, in terms of the evolutionary story, life kind of is, when I was reading the book, it kind of made me think of it's like when you're driving a manual car and you're getting out of first to second, and you're kind of not really getting it, and you kind of get out of first, you get to second, and then you kind of get to third, and then you're just flying, right? Mm-hmm. Because then you get to 500 million years, and this is where we start seeing, octopuses, which we still have today, obviously, and many, many creatures. And so, but how do we get from, so that story, the Cambrian explosion or rumble, that happens, and then we're getting the hard shells, we're getting the backbone, we have some sense of a digestive tract. So these are all these things with life as Rodinia is breaking up, but then we get fish and we get vertebrates. And so how do we get from those kind of sponges, and then we get some, mollusks or shell creatures, so now we're having full fish and vertebrates? How does that piece happen?
Well, I don't want to go on at great length about this, because this is one of my particular pet subjects, is the origin of vertebrates. I mean, I've written a couple of books on it. And it's one of the great puzzles in evolution. It puzzles Aristotle, is that how do you get from squishy sea creatures to vertebrates with backbones and brains and so on? Right. And it's still a matter of great debate in evolution. But what seems to have happened is that vertebrates invented a kind of chassis in which at the front was a filter feeding head, where stuff would come in through the mouth and be filtered out through the gills at the side, attached to a tail which was based on the notochord, which is the precursor to the backbone, which muscles could be attached and could swish around. So what you'd have was a kind of animal that generally was buried tail first in the water, and filter fed with its pharynx. And yet if it was disturbed, it would suddenly swish away, swim away very quickly, and then bury itself tail first somewhere else. Now, there's still animals today that do this, the Amphioxus or lancelet, that looks like an anchovy fillet. I mean, it looks like a little fish, but it doesn't have fins or a head or anything. And that still does it. And then there were the kind of tunicates, the sea squirts, that are kind of deconstructed the whole thing. The adult is one gigantic pharynx that sits in the same place. And the larva is just one tail that flips around until it finds somewhere it can grow into an adult. So these two things became the ingredients of vertebrates. And what happened was these two ingredients, the filter feeding pharynx at the front and the tail at the back, kind of grew together. So you have an animal that's got a backbone all the way from the front to the back with a head at one end and a mouth, which was filter feeding, but eventually became predatory. And that is the fish. So you get these tiny little fish, and they started to have amazing things like brains and eyes at the front because they were predatory. The vertebrates are this kind of riff on this filter feeding thing with tail. Vertebrates are the predatory riff on this. So they integrated the whole thing. So the tail wasn't just an escape mechanism, it was a dedicated means of propulsion. And the filter feeding head became a head to eat other animals. And of course it had a sensory organ so it could see where it was going. And that's how fish came. So at the end of the Cambrian, there were little fishes, there were fish in the water, and some had started to evolve armor plating. So the first vertebrates were there in the Cambrian.
And we have, so there's just this, again, this at the end of the Cambrian, this is, kind of spawning out, and all these things, are happening. And this is obviously taking place over millions of years. But then we get to this huge step from water to land, right, in our evolution of life on Earth. And so if people are listening, you can kind of, I mean, this is kind of how your book reads, which is really nice, but even in the conversation is, you're just seeing how things are just continuously expanding, right? We're getting from, microbes, we're getting to sponges, we're getting to vertebrates, and now we're getting to something completely different. And so I guess the one question is how do we get from water to land, or animals that are evolving from being water-based to land-based? And was that a factor of, as we're getting closer to Pangea, that now it's like, well, now there's more land mass above the water. And so there are things that if it's coming from the depths of the oceans, that there's this space of now evolution over, again, time can start to learn how to live in a new environment. And so is that kind of the linkage between water to land, or how do you see that evolution?
The thing is life always finds an opportunity to find it, to live in new places. So there are two things about land. One is a very positive one, and one is a very negative. The positive one is just an environment with no one else living in it. Woohoo! It's great, amazing for things to colonize. The other problem with land is it's, to the earliest organisms, it is about as difficult to colonize as empty space. Because for an animal that's lived in water, where oxygen is dissolved in the water, so for example, on land, there's nothing to hold you up. So you can't be, there's no buoyancy in fresh air. And the other thing is, you have to actually suck the oxygen out of the atmosphere with some wet surface like a gill or something without desiccating. And then of course there's the sun, so you'll be fried. So you're going to be fried, asphyxiated and crushed by your own weight. And that's within 2 minutes of getting onto land. But this thing didn't happen all of a sudden. There were lots of little steps. And the first things that came onto land were well over 1 billion years ago. There are fossils of little bacterial crusts that lived in fresh water. They lived in little ponds and streams, and they lived as crusts above the seashore as the tides went in and out. And they got the intertidal zone is a very harsh environment because the sea keeps coming up and down, and there's all sorts of variations in temperature and salinity. So little creatures were becoming evolved to the intertidal zone, and these were seaweeds and very small creatures. So, and then as part of this, sort of just after the Cambrian explosion, maybe in the Cambrian itself, plants, simple plants came onto land, associated with fungi, which helped mine stuff from the earth. Now, there was no soil, because it's action of living things that make soil. The dead organisms rot down, roots burrow into it, they turn the minerals into different things, they fill the stuff with humic acid, they dissolve minerals. So plants and fungi had to come in to create soils and leaf litter, and they were very small. I mean, they were tiny little creeping things. The idea that life came onto land in the Cambrian used to be very, very, very heterodox. It was promoted by an amazing woman called Jane Grey, who's unfortunately no longer with us. And I love Jane because she was the most ornery person I've ever come across. I used to get papers on the early colonization. I'm sorry about this digression.
No,
this early
fine.
colonization of land, and the authors would say, if you're going to send this to external peer review, send it to whoever you like, but please don't send it to Jane Grey. So, of course, I didn't send it to Jane Grey. But I thought, this was before the internet, I couldn't look her up.
Right.
And I thought, who is this Jane Grey that people don't want me to send things to? So the first opportunity that arrived when I got a suitable manuscript that didn't rule out Professor Jane Grey, I, of course, sent it to Jane Grey. And then I realised why nobody wanted to send it to Jane Grey. This referee's report was so rude, it could strip paint off a barn door at 50 paces. I had to write back to her and said, could you actually take all the expletives out? I mean, the authors are going to read this and cry. And after that, I got on with her like a house on fire. But unfortunately, she's no longer with us. Anyway, she actually pioneered the idea that life was on land in the Cambrian, and nobody believed it, partly because she was a woman, and also because she was extremely rude and unpopular, and nobody liked her because she was, she told it like it was. Anyway, plants came onto land very slowly, first just to the edges of lakes and rivers and little encrustations, and they formed leaf litter as shade, and then tiny little bugs came ashore, little tiny things like the sort of things you see that irritate you when you're on the beach, like sandhoppers and things like millipedes were very early, and spider-like things. And they would fight tiny little to the death battles under all the leaf litter. But then plants evolved a way to counteract gravity. They evolved woody tissue and they shot upwards. And this was a huge evolutionary pressure, because if plants are shooting upwards, it will shade other plants from the sun, and they don't want that. They want a piece of the action, so they shoot upwards as well. And so within a few million years, there were forests of trees. I mean, nothing like trees we see today, but there were forests. And of course, they would produce leaf litter and detritus, and that would make more soil, and then more little animals would crawl out underneath. And then what we're interested in is, of course, the tetrapods. These are the vertebrates that came onto land.
Right.
Now, tetrapods include every vertebrate that isn't a fish: amphibians, reptiles, birds, mammals, ourselves. But most vertebrates are still fish. And there are fish that live in the deep sea, and there's fish that live in shallow water, and fish that live in lakes. Well, tetrapods are really fish evolved to live in water of negative depth. So they started as kind of crocodile-like creatures with fins that evolved digits, but they were still pretty much tied to the water. Although they had legs with fingers and toes, they couldn't have got far on land. They had internal gills, but they would have lived in very shallow, weed-choked water, and they were ambush predators. They probably had lungs. In fact, fish originally always had lungs. They had lungs, and they were using their gills less. So they could have, lived out of water for a bit, but they couldn't have moved on land because they were still very finny. And it was
so they're an intermediary species of sorts.
Yeah, there was like Neil Shubin's Tiktaalik, the fishapod.
Yes,
that was exactly like one of these things.
Yeah.
So there were some very big fish that were definitely fish that lived in this mode of shallow water ambush predator. And there were these early tetrapods that also, there was another extinction towards the end of the Devonian period, where a lot of the fish died out, but some of the tetrapods survived, including these ambush predator types. And of course, some of them came onto land. Some of them were more land capable than others. There was a whole diversity of them. And some of them came onto land because land was a great place because it was full of wonderful insects to eat. And forests to shade under. And they were never too far from water because, of course, they relied on water to breed. So they never got too far from water. And these were the distant ancestors of the ancestors of the ancestors of what we would call amphibians today. And they were already quite diverse by the end of the Devonian period, about 360 million years ago. There were some that were pretty much good on land, some that wouldn't have been on land at all, some with different kinds of digits, different numbers of digits, and some that had even lost all the digits they'd so lately acquired and became completely aquatic again, like little water snakes. So there was a huge diversity of tetrapods, more or less adapted to living on land. So the commitment to land wasn't very strong for a very long time. It wasn't as if there was a brave pioneering vision. I mean, one of the books that is a wonderful cartoon book, these days we call it a graphic novel, called The Cartoon History of the Universe by Larry Gonick. And at the very beginning, I was talking about the expansion of the galaxies, and he said there was, of course, the paranoia theory of universe expansion. All the galaxies are flying away from us because they hate us. That was that one. But he also had this image of two fish climbing onto land, and they see these little insects scuttling around. And the first tetrapod says, "I will be the first on land." And the second tetrapod saying, "Hang about. That's not true, is it? Because the bugs were here first." And the first tetrapod says, "They won't get the credit because my descendants will write the book." But so the land was there waiting for tetrapods to colonize it. But the funny thing was, you'd think they come out of fresh water like frogs do, but they didn't. They came out of the sea. So they're a strange kind of amphibian of a kind we don't know today.
Yeah. And this is really, it's not broken up this way, but it kind of feels that way in terms of the book, is that, you have the very early beginnings of the planet. And then we kind of get to like the really, fun stuff I think that people really like. Although I find every period has its own unique aspects to it. But, then we get to the idea of how did life, all these small beginnings, and how did life make such large creatures, if you will? And so how do we get to mammals? And then how do we obviously get to dinosaurs, which is super fascinating. So before we get there, maybe explain a little bit the importance of the lysopods, right, for the environment, and
the lycopod forests.
And how that's not only important for the Earth, but it was also for many of the emergent animals that were during the Carboniferous period.
Now, that's the Carboniferous period. I mean, it's called Carboniferous because that's where coal comes from. And the Carboniferous and the subsequent Permian period, they had these. Now, in a brief period, of 70 million years, that's where almost all the coal on the Earth was formed, in that period. I mean, there's coal in other places, but most of it comes from that period. And it comes from the coal forest, and it comes from these amazing plants called lycopods, which are incredibly profligate in their use of carbon. Now, their relatives, they're called club mosses, and their relatives still around today, but they're quite small and live around ponds and things. Like horsetails, the field horsetail, you get that today, and they're only so big, but they used to be big trees.
Mm-hmm.
But now when we talk about trees, we think of creatures that have a great woody structure and they reproduce each year by producing flowers and seeds and things. Right. But the same woody structure stays there all the time. Mm-hmm. But the lycopods would be just stumps in the ground. And each time they wanted to reproduce, they would produce an entirely new woody structure. Mm. It would take some years to grow and then mature and shed spores, and then it would die and fall over, and then another one would form. Mm. So just to reproduce, it had to use all this carbon to produce these huge trunks, tens of meters tall. Mm. And they had to do it each time they reproduced. Mm. And when they reproduced, the trunks used to just stay there. And they didn't have leaves all the way up. They had a little frond of leaves at the top. So you used to just get these bare trunks hanging around in a state of more or less decay, falling over. Mm. And some of the trunks were buried entire. And it was the accumulation of all these tree trunks that created the coal measures, that created all the coal that has been mined today. Really thick and, entirely carbonized deposits. But because they used all this carbon, they again sucked carbon dioxide out of the atmosphere, and that produced another ice age during the Carboniferous and Permian, mostly in the south, because most of what became Pangaea in a few million years was around the South Pole. And so that had glaciers around the South Pole. So it produced a long ice age, not as severe as all the other ones, because even though there was more land, the sun was that much hotter. Mm. So the lycopods were important, but they were the landscape in which a lot of the early tetrapods and the earliest, the ancestors of the reptiles evolved in. Mm. They looked like It looked like the Western Front in the First World War. There were all these kind of craters that were formed of the old trunks of the lycopods, and occasional ones sticking up out of the air, mostly with no leaves on. So it would have looked like a most appalling wasteland, but it was very, very rich in life and diverse life at the bottom. And all these little shell holes would have been wonderful ponds for the insects and tetrapods and so on.
And you get that when we talk about many of these tetrapods and these animals now on land. You describe in the book the ammonite egg. Am I saying this right?
Amniote.
Yeah, amniote like egg, which was essential for vertebrates on land. And so how was that so essential? And maybe describe that process.
Well, when you think about an amphibian in your pond, in your yard, they will lay spawn. Yeah. These little jelly eggs. And the problem with spawn is they make an easy, tasty snack for anything that is passing by, full of protein, can't run away, absolutely lovely. So amphibians have, over the years, come up with all sorts of clever wheezes to make their eggs to give them a better chance of surviving. They will lay them in little out-of-the-way places, such as holes in trees, or they will even incubate them inside the adult themselves. And they even have some kind of placental reproduction, some of them. Some of them even have lay them on tree branches over water, so that when the tadpoles hatch, they immediately plop into the water. So the amniote egg was just another mechanism to help to increase the odds of the baby amphibian growing up. Basically, the amniote egg is a private waterproof pond. It's a private spa just for one egg. So what happens is you've got the little baby embryo, and it's got its yolk to nourish it, but it's also got a waste sac like a diaper, the allantois, that collects all the waste. And it's got this membrane all around it called the amnion that kind of shields it all. And around that is the shell, which in the earliest reptiles was kind of a bit leathery, probably. But the key thing is it was waterproof. It wasn't airtight because air had to get in, but it was waterproof. It was like a space capsule that allowed the creature to live on land. Now, this was just another way for amphibians to have to give their young chances of growing up, because if they were in this little egg, it would be harder to get at because it would have this shell. but also it meant it could bury it in places that weren't tied to water. You could bury them in a hole in the ground where no one would look, rather than having them in open water.
Yeah.
And so the amniote egg was the key, the final key to the conquest of the land by tetrapods. It took a long time, but we still have it to this day. I mean, the human embryo is basically a little amniote egg. And, you know, when a pregnant woman's waters break, that's her amniotic sac rupturing because the baby is ready to come out. Except people don't have a shell. The shell is formed by the entire human. So the amniote egg was the key to the success of vertebrates on land. Amphibians did have a stab at being really good land animals, but they mostly retreated to the water after the end of Permian extinction. Another more extinctions, huh? It just keeps happening.
Yeah, well, that was my next question there, because as you walk through the book, we have the Cambrian period, the big explosion, life on Earth. There's a few other periods in there. We have the Devonian piece, this Carboniferous kind of collapse, if you will, and then we get all the way to this Permian period, which is kind of the great dying, right? It's another extinction, and so and at this time, this is where we start to see Pangea, right? So we have the Pangea, it's this ever-changing environment of the Earth. And the Permian period is kind of the great dying. And so I guess what was the extent of, so going back to the first part of the conversation, as we know, disaster, and out of it, after that big disaster period, there usually comes life. There becomes more, these things that happen, right? And so what was the extent, I guess you could say, of this great extinction period, and how close were we to losing all of life on Earth at that point, and then reclaim it?
Well, the Permian was the greatest the end Permian was the greatest mass extinction of the past 500 million years. There may have been other ones. I mean, back in the remote past, when some clever bacterium invented oxygen-producing photosynthesis that killed virtually everything else, because oxygen is a lethal poison to many things. But, that was so long ago, and we have no fossils of it. But the Permian is the greatest mass extinction for which we have good evidence that happened 250 million years ago. And it was a kind of perfect storm of lots of things happening together, which, if they hadn't happened together, might not have been quite so severe. I mean, the first thing, you mentioned Pangea. Pangea coalesced together. And that meant there was when you have a lot of small continents, each with their coastlines, and it's around the coast that most animals live in the continental shelf. When you have that all coming together, you have a big continent, but there's less coastline to go around. So there was a lot of competition for the coastline. Also, after the lycopod forests, plant life took a bit of a tumble. And so plants weren't producing as much oxygen. I mean, one of the benefits of the lycopod forest was, plants, they suck in carbon dioxide, but they produce a lot of oxygen. So there was so much oxygen in the atmosphere that lightning strikes could set forests alight even if they were waterlogged. And there was so much oxygen that insects grew very large. There were dragonflies as big as seagulls, and millipedes the size of carpets, and scorpions the size of dogs, and this kind of garden of earthly delights in which the early reptiles grew up. But then after that, plants went into a bit of a decline, and there was less oxygen around. So moving around on land would have been like walking in, even at sea level, would be a bit like trying to breathe in high mountains now. So it was a bit of a puff and a squeeze. Also, a lot of Pangea was very harsh. Because because it's one big landmass, a lot of it's far from the sea and would have become very, very hot desert. So Pangea wasn't, there were wonderful parts of Pangea. Don't get me wrong, there are places you would have loved to go on your vacation, but a lot of it was pretty inhospitable for most things. So life was already under a degree of stress. And then in the Pangea, there was a kind of land that time forgot. There was the continent of South China that lay off the kind of east coast, still had lycopod forests in. It was a kind of relic. But that was all destroyed when some magma came up from the earth, and a huge volcanic province, a bit like people are afraid Yellowstone might be, erupted onto the Earth, producing magma. And that produced lots of gases. It produced carbon dioxide that increased the greenhouse effect and boiled everything, and all sorts of other noxious gases. And that created, that knocked life back a bit. And it still hadn't quite. So first of all, we've got Pangaea's not very, rather inhospitable, not very full of, not very breathable. And then we get this thing in South China. And then when a few 100,000 years later, when the life hadn't recovered from that, a bigger magma plume erupted in what's now Western Siberia on the main landmass of Pangaea, and coated an area the size of the continental United States between the eastern seaboard and Denver in basalt.
Oh my goodness.
Thousands of meters thick. And that produced more carbon dioxide, which shot up the greenhouse effect, so everything boiled. And then it produced all sorts of other lovely things like mercury vapor. And because the plants were already under stress, they couldn't soak up the carbon dioxide. And it also, there was a lot of acid rain. And so life on land was kind of washed away because the trees all died and they were all washed into the sea. The sea was full of dead bodies, so all the oxygen was sucked into there, so the sea became stagnant. So everything kind of died. And it killed about 95% of all things in the sea and over 70 on land. So it was almost not back to the time of stromatolites, because if there are no other creatures around, stromatolites could survive anything. So life it takes an awful lot to kill life on Earth. But the end Permian was the closest that the Earth has come. And it took some millions of years to recover, but oh boy, when it did, it really did.
Yeah.
After that was the Triassic, the unjustly forgotten about Triassic period, which was a real carnival of life.
Yeah. Well, it all starts to kind of naturally, I guess you could say, tell its own story, right? It's like, okay, there's a big catastrophe. What's going to happen next? And so we have the Triassic period, which is really about, my view is, it's just kind of this rebirth, right? It's kind of coming from the ashes. And so how, in this period after the great dying in the Permian, how in the Triassic, which for listeners is the kind of precursor to the Jurassic, right?
Yeah.
But in the Triassic, how is Earth, changed, and how are the animals that have survived? How are they now pushing for life on Earth and another kind of explosion of sorts?
Well, the Triassic was a great period for reptiles and also other things like insects. There are most amazing insects in the Triassic, but but the reptiles and the early mammals, animals of the kind that still survive today, most of them originated in the Triassic. Turtles, mammals came from the Triassic. The earliest things that would be snakes and lizards, they came from the Triassic. And the earliest kinds of modern land plant were found in the Triassic. But there was a lot of experimentation. There was an awful lot of aquatic reptiles. I mean, the turtles we see were part of an amazing diversity of turtles. There was turtles with belly plates but no shells, turtles that look most unturtle-like except for the beak. There were all kinds of fake turtles, pretend turtles and mock turtles and teenage mutant ninja turtles and turtles of all kinds. But there were other amazing marine reptiles that lived around. Perhaps the most magnificent were the ichthyosaurs, which grew to be so much like what we would look like as dolphins. They were completely aquatic. They gave birth to live young at sea. And in the Triassic, they survived till almost the end of the age of the dinosaurs. But their heyday was the Triassic, where they had 21-meter whale-sized ichthyosaurs, which were the largest marine reptile ever in the Triassic. Also, they were the first pterosaurs, pterodactyls. They took to the flight, along with a lot of other flying reptiles. Gliding reptiles, they came from the Triassic, and a lot of other really weird reptiles that lived and died in the Triassic. Now, I think that now, of course, the most famous product of the Triassic were the dinosaurs, and they came towards the end. But because the dinosaurs have become so famous, it kind of eclipsed all the other Triassic things. So people don't know much about the Triassic, which is a great shame because although the Age of the Dinosaurs was magnificent and fascinating, in many ways the Triassic was much more fun. But it was a 50 million years of really the circus coming to town, the Triassic. Of course, it ended with another extinction, where Pangaea was starting to break up. There was a huge rift valley on the eastern seaboard of the United States. Now, the eastern seaboard of the United States seems to be a weak point in the Earth's crust. You know, millions and millions of years before, it was a kind of fracture zone that had come together to squeeze out an earlier version of the Atlantic Ocean. And then it glommed together to become Pangaea. And then more or less along the same line, you know, probably underneath your house, all the way from the Carolinas up to the Bay of Fundy, was a rift valley opened. And eventually the sea entered and there was magma and the usual stuff. And that was the end of the Triassic. But it was one of the big 5 mass extinctions, but nowhere near as catastrophic as the Permian. Although the Triassic, the end Permian saw the end of amphibians that had any major pretension to land life. And it saw the end of a lot of animals. In the Permian was the heyday of what was called the mammal-like reptiles. These were a whole very varied group of mammals that a distant offshoot of which became mammals. They include Dimetrodon, the sailback reptile, and a lot of other things called therapsids, which is not to be confused with therapists. And one of the very few therapsids to survive was this amazing creature called Lystrosaurus, this pig-like creature that had this go anywhere, eat anything attitude. And at the beginning of the Triassic, most animals were Lystrosaurus. It was just one of those lucky survivors because it could burrow out of the way of anything and wasn't fussy about what it ate.
Was this considered the first mammal of sorts?
Oh, no. These were called dicynodonts. They were an early offshoot of this large group of the therapsids that one group became the mammals called the cynodonts. And we can come on to those later, I guess.
Is it well in terms of, you know, in the Triassic, is this where we start to see some of the first mammals, you know, kind of moles and rats and things that lived underground and things like that?
Well, they would have looked a bit like that, but they were, of course, only very distant relations. But they were the thing about mammals is they evolved in a particular way. There were these therapsids called there were some therapsids that were as big as cows and elephants, but the mammals evolved from a group of these therapsids called cynodonts, meaning dog teeth, and they had very varied dentition. And they got smaller and smaller and smaller. They just evolved to be smaller. And as they got smaller, they got furrier, and they had whiskers, and they had a complicated middle ear joint that allowed them to hear very high-pitched sounds that reptiles and even birds can't hear. And also, they became nocturnal. So things like smell and touch and hearing were more important than vision. And 2 of the earliest mammals that we know about, Kuehneotherium and Morganucodon, lived in the Triassic, but they lived in that part of Pangaea that was almost inhospitable desert. And they were nocturnal because they stayed out of the heat of the day. They would come out only at night. And because they could control they were warm-blooded, and that is they could regulate the heat of the day. They could regulate their own body temperature. They didn't have to hang around to warm up in the sun before they could do anything. So they were always the first out to munch on the latest morsels, you know, any stray insects or dead lizards or anything that were around. So mammals evolved a knack of being nocturnal, which not many other creatures were, because the reptiles are very visual creatures, and particularly the dinosaurs that came. But of course, by the time the mammals had evolved and wanted to start getting big again, the dinosaurs had evolved and stopped them doing it for 160 million years.
And so I've read many different places that we have some of these early mammals that were, at least for a time, cohabitating with dinosaurs in the Jurassic, and there were some, again, living side by side of sorts. Again, these are kind of these early kinds of mammals. But I guess we can move from end of Triassic to the Jurassic now, and it's all in the book, which is really great. I mean, it's a really nice kind of summary that you give of dinosaurs in the book. But some of the really cool things is that you detail, like, how did animals be small and then they just grew and just became large. I mean, dinosaurs were tremendously huge. And you talk about dinosaurs' anatomy, right? Such as being built for flight, being bipedal, they have an air cooling system, their breathing, and other unique features. So maybe just tell us a little bit about the kind of physiology, if you will, I guess, of dinosaurs and how they were in this period.
Well, dinosaurs, right from the beginning, were always built for flight. I mean, dinosaurs and their ancestors had this amazing breathing system. They don't just breathe in and breathe out. Well, they do. But once they've breathed in, the air doesn't come out again immediately. It circulates around all these incredible air sacs that penetrate all through the body, even into the bones. And what that does is that cools the internal organs, particularly the liver, which is the main factory of the body, and that's the main thing that breaks down food. And that creates a lot of heat. Now, in a large dinosaur, that was the size of a car, but they had it was air cooled. It had an air sac next to it, which meant it could shed its heat directly throughout the lungs rather than into the blood and then out of the blood again, and then therefore compounding the problem. So dinosaurs could grow to a big size without boiling themselves from the inside out. Because one of the problems of big things is as you grow, there's less surface area in relation to the volume of anything. So if it's the same shape. So as an animal grows, there's more insides that have to be serviced by air, and waste have to be excreted. And so that was back in the early days, that was another impetus to develop the mouth and the anus, because it was an easier way for an animal at more than a point to get things in and out. So when you get to the sides of a dinosaur, you have these immense lungs and air breathing systems. Now, birds have these now, so do many kinds of lizards. It seems to be a reptile thing that mammals don't have. The mammals have a different form of breathing. So it was the air cooling system that was the key. And also another thing that they had, dinosaurs started as bipeds. There were a lot of animals that were bipeds in the Triassic. There are lots of kind of strange friends and relations of crocodiles that were bipedal, and dinosaurs were just another one of this lot. But they perfected it, and they did it. They kept their backbone horizontal, but they had a long tail sticking out the other side, which cantilevered the whole body over the hips. So they could stand and move bipedally without any effort, because they were just so finely balanced. But that requires a great deal of control, which meant that dinosaurs generally had quite large brains. I mean, one thinks of dinosaurs as being very dim. Well, some of them probably were, but certainly the smaller bipedal ones were very, very active creatures. And another thing that dinosaurs did very early on was evolve feathers. This has only been certainly known since 95, 96.
I talked to recently Richard Prum.
Yeah, I know. I heard that.
I believe he was really instrumental. He developed a certain taxonomy for. I mean, he's genius when it comes to birds, but not only the birds having feathers, but having colored feathers.
Yes.
I mean, it's just I remember when he was explaining that to me. I mean, it's just absolutely marvelous to hear that.
Birds have great color vision, which mammals mostly don't have. I mean, we primates are rather unusual in having trichromatic color vision, but birds had it, and dinosaurs almost certainly had color vision. And quite recently, it's been found that dinosaur feathers were colored.
Yeah,
I mean, they had patterns. So feathers, I mean, who knows what feathers were used for? They certainly weren't used for flight to begin with, because some of these creatures that had feathers were about as as aerodynamic as a sack of rocks. I mean, they weren't aerodynamic. So what would feathers have been used for? Well, they would have been good for sexual display. They would have been good for display to colourful things, to colourful animals. I mean, they were just like birds are now. And another thing feathers are good for is insulation, especially if you're small, because dinosaurs, like mammals, generated their own heat. Now, if you're a big dinosaur, you don't need feathers to, your problem is getting rid of excess heat. But if you're small, the problem is not wasting all that heat you've expensively generated. You've got to keep it all in. So it's possible that a lot of big dinosaurs had feathery chicks, and the feathers were shed as they grew older. So that's quite possible. Dinosaurs were even built for flight. I mean, even the very largest four-footed dinosaurs weren't really giant lizards as we used to think of them. They were gigantic four-footed flightless birds. That's really what they were like. And so dinosaurs took to the air sometime in the Jurassic, some of the smaller predatory kinds. And Archaeopteryx, the iconic first bird, was really just another feathered dinosaur. And all this has happened in, all this amazing change in knowledge has happened relatively recently.
Yeah, it's interesting how far, with paleontology and for many different disciplines, how we keep finding out many things, and the new technology that's used now is just quite incredible. I have to ask, at this part, talking about dinosaurs. I mean, obviously we have a handful of films about dinosaurs.
One or two, yes.
Yeah, one or two. Do you like the Jurassic Park series?
These kind of obscure art house movies that people have seen. Yeah. Oh, I love them. I love them. Yeah. I mean, they're films. They're great fun. I remember going to a press screening of Jurassic Park in a huge cinema in central London, and with my wife, we both went, and we sat in the front row and were absolutely terrified by this Tyrannosaurus Rex that loomed over us. It went rawr, and we went ah. So and it was absolutely marvelous. But then it's Spielberg, and I think he's a genius, and so then it was a pioneering film. But then, of course, you have the of course, since then, dinosaurs have been found to be quite different. They've been found to be feathered. And so you have Jurassic World, where you still have Jurassic Park-style dinosaurs. They're not feathered. But I don't care. I mean, a film's a film. And, in the Jurassic, I haven't seen the latest ones, but in Jurassic World, they kind of did a reference to that, because the biggest, fiercest dinosaur was entirely a construct. It was just a mishmash of very fierce dinosaurs. So it was entirely artificial. So that kind of gave them the let out that they didn't have to have, the dinosaurs have to be feathered. But as great fun adventure popcorn movies, oh yeah, love them. I mean, they hang together as stories just about. So you hang up your disbelief at the door and you go and enjoy the film. I mean, I don't think you're supposed to think too deeply about them.
Yeah, no, absolutely. I think they are fun films. I recently rewatched all five, and I mean, again, I'm not just a kind of one of those people that says the old stuff is the best, but there's something about the original that just really has a timeless feel to it. It really just holds up over time. The new ones are fine, but the first one is just really, I don't know, it's just kind of special in some ways, and it's cool to really see it, even after all of the CGI technology we have. I don't know,
No, I know what you mean. I mean, I went to a press screening of Jurassic World in 3D, and so we all had these 3D glasses, and it was great. But of course, the thing about Jurassic Park was it was the first one, and so it was just new. Yeah,
the novelty of it. Yeah.
And of course, it's got classic horror adventure tropes. I mean, there's the bit where the little kids are in the Land Rover and they hear the thumping noise of the of the Tyrannosaurus's footprints, and they see the water glass.
Right.
I mean, that's just cinematic genius. It just conjures up a whole atmosphere without doing very much. And if you look at Jurassic Park and deconstruct it, basically it's a sequence of set pieces. and in between people are rushing from one place to the other. But it's a horror film. It's a horror fantasy. Being stuck in the kitchen with a ferocious predator, and oh yeah, brilliant. My kids were raised on it as well, I'm glad to say.
Yeah, no, absolutely. My daughter loves it.
My work as a parent here is done.
Yeah,
that and Monty Python.
There you go. So I want to ask before we move to humans. You talk about the fact that there were 25 groups of mammals that evolved during the time of the dinosaurs, and I think that's, like I mentioned, there's that some people are realizing that now, that that there were certain mammals that lived along with dinosaurs. I think people used to think that it wasn't the case, and so how is that important, I guess, for the evolution of mammals? How do tropical forests fit in here, and how do we understand how humans? How do we understand that mammals, survived the big asteroid that took out the dinosaurs?
Well, the mammals became nocturnal, and they became very good at live fast, die young strategies. Like shrews and mice don't live very long, but they produce immense amount of offspring, and they live at a most incredible pace with very high metabolisms, and they have to eat their own weight in insects every night or they'll die of hunger. I mean, mammals were very good at that small nocturnal niche. But because animals that live fast also evolve fast, so all these groups of mammals kept evolving, that kept trying to break out. At least 25, and some of them really did cause the dinosaurs a bit of a problem. I mean, when dinosaurs first went up trees to fly out, there were at least two kinds of gliding mammal already in the trees, and there were mammals that were a kind of early versions of what would now be beavers that lived in the water. And there were mammals that were as big as badgers that would eat baby dinosaurs. They would go and prey on dinosaur eggs. And so there were quite a few of these mammals, but only of all these, at least, I mean, we keep discovering more, but of all these at least 20 groups, only 4 survived the end Cretaceous extinction. There were the placental mammals, which is most mammals. There were the monotremes, like the egg-laying platypus of Australia. And there were the marsupials, which have evolved a kind of handy halfway house between egg-laying and life-bearing. And there were another group called the multituberculates, which are a bit like rodents. And they survived until real rodents came along and drove them to outcompeted them. So the multituberculates lived until about 50 million years ago and then died out. So forests, when the dinosaurs died out, forests and trees became very important. I mean, you had Patrick Roberts talking about it. In the Eocene was a time when that was, we've had the Earth as molten lava, we've had water world, we've had snowball Earth. In the Eocene, it was jungle planet. It was jungle all over from pole to pole. Trees everywhere, very untidy sort of place. And of course, they had lots of things living in the trees and a lot of mammals living in the trees. The earliest placental mammals were tree livers, and probably most of the others as well. About 55 million years ago, it was called the Paleocene-Eocene thermal maximum. It was really hot, very jungly. And since then, the Earth has only been cooling ever since. But it was in those trees in the Eocene that the earliest primates evolved. And they suddenly re-evolved colour vision because they were interested in fruit and eating fruit. So they could see red fruit because they could evolve the colour vision. And they were climbing animals. They had opposable thumbs and could scamper around in the trees. And that was the primates. But of course, as the Earth cooled and thinned out, primates had to do more than live in trees. They had to live in a more varied mosaic environment. They had to get down on the ground occasionally, if only to scamper from one tree to another. And then monkeys and apes evolved. The big change happened about 30 million years ago when Antarctica, a fragment of Pangaea,
Right.
moved over the South Pole and became glaciated. And that was the start of the ice age in which we currently live. When Antarctica drifted over the South Pole, because then after many tens of millions of years, permanent ice caps had returned to the Earth. Mm-hmm. And that caused the climates, even in the tropics, to become more seasonal. There was more grassland, more plains. Little scampery forest animals that looked like squirrels evolved into the ungulates that cropped this an amazing new kind of plant called grass, which evolved around then, which had its growing bit at the bottom. So if you crop the top of it, it wouldn't die. It would just keep coming up from the bottom. That's how grass worked. And then you had much larger carnivores, and then some of the apes started to join in, and some of the monkeys. Some monkeys still live on the ground today, baboons and macaques. The primate lineage, along with a lot of other animals that came out of the Eocene forest, started to experiment with different forms of life, and a lot became larger. The most amazing transformation was the whales, who within 8 million years became completely aquatic from a kind of dog-like ancestor. Amazing.
Yeah, which is super spectacular in terms of whale evolution, and then obviously, like you're mentioning, with the primates as well. And so we have primates that come onto the scene, and all different types of primates. And so you're right. When I was talking to Patrick about this, he talked about that primates that were living at one time, and then they died off, right? And so and now there used to be many primates at one time, and then now we have few, right? So why do you think?
Yeah, well, there used to be lots of different primates, but guilds and generations of primates have come and gone. I mean, all the primates that lived in the Eocene, all those kinds of primates, the adapids and the Homo and so on, they're all extinct. But there used to be a lot of apes. There were old world monkeys, and quite soon evolved apes, large old world monkeys without tail, until you couldn't move for bumping into apes. You just trip over them everywhere. It was like Planet of the Apes. About 10 million years all over the old world, never in America. There were apes everywhere, and not so many monkeys. And nowadays there are not many apes and quite a lot of monkeys.
Right.
But I think that's just the way the cookie crumbles. I mean, there are all sorts of little random things that happen. Apes and monkeys became adapted to a kind of life in a wide variety of different environments. Apes lived in deep jungle and deep forest, and also on open country. I mean, the hominins became the kind of open country apes, and that tended to live in more what ecologists call mosaic environments. They were a little bit of a few trees here and there, some bushes, a bit of water going through, kind of mixed environments, rather than in a deep forest or in a completely open desert or somewhere like that. So about 10 million years ago, there were loads and loads and loads of them. And I think what happened was the Earth cooled some more and became quite hard to live in for animals like that. So apes actually were forced to do one of two things. One is they went back into the deep forests to live a kind of theme park existence, where they gorillas and chimps and orangs, where they're still hanging on.
Right.
Or the others is they became much more committed to living in more open country with not many trees around, and moving around on the ground more. And those apes tended to be the hominins.
Right.
Which happened around 7 million years ago in the Miocene.
And so this is really where we start see many branches here in which we get to humans. But I guess the one question I have about that is the Homo erectus, so there's many different precursors, obviously, and many in the hominids group, right? Australopithecus, obviously there's many different classes, but Homo erectus was huge. I think they had bigger brains. They were able to harness fire. They were mostly bipedal. But they were the ones that really did kind of start walking out of Africa, start walking more about the earth. And so, what do you think it was particularly? I mean, Homo erectus is always a really fascinating class. What is it about them that you think that caused them maybe to just start saying, let's just explore, let's wander? Was it the cognitive capacity, if you will, with their larger brains? Was it that they were fully bipedal, or at least they could be if they wanted? Maybe something else. I mean, it's hard to kind of tell exactly, but what do you think was the ideas kind of rummaging around their brains to start being travelers?
Oh God! I mean, there are as many answers to this as there are people. But I think looking at the evidence in a long way, I think the main thing about Homo erectus was it evolved to be a predator, a savanna predator, a pack hunting savanna predator like a hunting dog or a lion or hyena. Before that, hominins were kind of omnivorous or purely vegetarian, and they used to scavenge carcasses and they used to dig for vegetables. But Homo erectus became more of a predator. Rather than scavenging carcasses others had left behind, it would actually hunt in its own right, and it would hunt cooperatively, just like hunting dogs do today. And I think one of the main things were that although hominins had been bipedal for millions of years by that time and could walk, Homo erectus was one that actually started to do something new, which was run. This was explored by my friend Dan Lieberman, who's a professor of anthropology in Harvard, who's known to everyone as the barefoot professor. He runs marathons and he does things barefoot, and he explores how humans walk around barefoot in the wild, and he does the mechanics of that.
Didn't he write the book on exercise recently?
Yes, he did.
Yes,
he did. He did. Yes. You ought to get him on. He's great.
Absolutely.
He wanted to explore the myths of exercise, and I read an early version of that book. It was great. Well, Dan said that a lot of the adaptations you see in modern humans are not, which would have come from Homo erectus, because Homo erectus was the first hominin to have a more human body shape, would have been adaptations for not just walking, but running. Human beings have a distinct neck, which allows the head to move independently of the shoulders. And also human beings have more of a waist. They're not the older one. The other animals were more pot-bellied with shorter legs and longer arms. Homo erectus had a neck and a waist with longer legs and shorter arms, but meant as it ran, its legs would move in counter rotation to the arms, while keeping the head directed forwards. Also, Homo erectus was less hairless and had more sweat glands. And one thing that human beings are not great sprinters. I mean, apart from Usain Bolt, human beings can sprint for a short distance.
Right.
But many animals can sprint much faster for a short distance. But what human beings are very good at, even today, is endurance running. I mean, you see this today with, the runners from Kenya and Ethiopia. And, I've been to Kenya. People run around all the time. That's the way people get around. I mean, they just do it. But humans are good endurance runners, and like hunting dogs, they can keep pursuing some game like an antelope for kilometer after kilometer after kilometer, and they won't allow it to rest until it just literally falls over from heat exhaustion. That's how humans can hunt, but they have to do it cooperatively, because even an exhausted eland or Cape buffalo or something is no match for one puny human. So they have to do it cooperatively. So Homo erectus was specialized for this kind of cooperative savanna predator niche. And it spread out of Africa because it was following the game. It went wherever the game went. And it wasn't, it had although it did have a home range, if the game had gone somewhere else, it would have to follow, otherwise it would starve.
It's interesting to me. Again, the cooperation thing is a really cool recurring theme, but it's always interesting to me where you know, what could we do if we got in a time machine and we went back to this time where Homo erectus was on the planet, and what would that look like, and how would it look so different? It feels like there's only these shadows of humans, you know. But
Yes.
How distinctly different would it look like? And it's always such an interesting kind of. It always just, again, I mean, it's one of my favorite films. It just reminds me of 2001: A Space Odyssey.
Yeah, wonderful.
Brilliant opening where it just really kind of puts you back. It's kind of like you go in a time capsule and you just kind of like, oh, this is kind of what it was like. And when they first start, you know, figuring out a weapon and, you know, and all that stuff, it's brilliant.
Well, Homo erectus, Alan Walker and Pat Shipman wrote a wonderful book talking about Homo erectus, and the title escapes me, but there was a phrase they used in it that Homo erectus would have seemed a bit like human, but it wouldn't have been look like human in its eyes.
Yeah.
It would have been like a predator, like a lion or a hyena.
Yeah, so
it would be sizing you up.
Yeah.
And it wouldn't have had language. But at the same time, they made stone tools, beautiful stone tools. They made fire, and they were expert hunters, foragers, and also they lived cooperatively.
Yeah.
They hunted cooperatively, and they probably would have had family groups waiting for them, you know, back around the campfire or the rock shelter or wherever they happened to be.
Yeah.
So the cooperation in humans probably began with the hunting parties of Homo erectus.
Mm-hmm. Yeah.
And a lot of other things too, to do with their sex lives, which of course are entirely speculative.
Sure. Yeah. It's absolutely fascinating. The more we learn about it, it just becomes more and more fascinating. So you also talk about in the book that immigration, right, or migration rather, is you know, was multiple small events that happened for humans. It wasn't like this mass exodus necessarily. And population genetics, I think, also is beginning. Population genetics is absolutely a spawning field now of all the different things we can look at, different waves of migration between places. And so, you know, what do we know about the time in which various human species lived on the earth at the same time? So maybe talk about this for a little bit, because this is something that when I was talking to Jeremy De Silva, he talked about this, which was so. I never really knew that, and it just kind of blew my mind. He's like, you know, you could see on the savannah, or you could see on certain places, you know, 4 or 5 or 6 different types of humans, hominids, whatever, at the same time cohabitating.
Yeah.
And that's just remarkable to me. You know, it's just because we're only the ones now left, and so we don't know that. And so you talk about that a little bit, I guess. For
almost the entirety of the existence of the human lineage, there have been more than one species. Now, but back in the days, sort of before 2.5 million years ago, when there was another step change in evolution related to climate, there were lots of these different Australopithecus type creatures, some of which were more vegetarian, some of which were more scavengers, and there were lots of different ones. Some of them were better up climbing trees, some of them were better on the ground, and they were all over Africa. Then after 2.5 million years, there was a step change in the climate. It became more dry. The ice ages started to ramp up in severity. And that's when everything was winnowed down to 2 kinds. There was a Paranthropus. There were several different kinds of these. These were the hominins that were totally specialized for vegetarianism. They had enormous, great crushing teeth, huge chewing muscles, and they spent a lot of their time grubbing up roots and grasses and chewing very hard stuff. And the other form was Homo erectus, which became specialized for hunting and for a carnivorous way of life. So basically the circumstances on the earth came to such a pass that hominins couldn't afford to have a dilettante existence, doing a bit of vegetarianism here and a bit of meat there. It had to, you know, cash in its chips and go one way or the other. Now, in the end, the Paranthropus ones died out because life just got too hard, and they lived and died in Africa. But by 1 million years ago or so, Homo erectus had spread throughout the tropical and temperate parts of the old world of Eurasia.
Right.
They got to China maybe as long as 2 million years ago, and into islands Southeast Asia, where they specialized. Where the island Southeast Asia has gone a different way from Africa. And I think Patrick Roberts might have alluded to this, is in Africa, the forests have withered away and become savanna. Yeah. But in Southeast Asia, jungle has come back again. Yes. So you've got all these little hominins marooned on islands, like the Hobbit Homo floresiensis. Yeah. And there was another one in the Philippines, Homo luzonensis, and who knows, probably a lot more, that became more forest creatures. And certainly the luzonensis one became more tree living. They reverted to a kind of more primitive shape. So the descendants of Homo erectus spread out through the world. So they had all these different forms in Southeast Asia. Then in Eurasia, there was this form which is very loosely called Homo heidelbergensis, which is only a kind of dustbin category, but probably a number of different kinds of human that were very big. They were bigger than people are now and very robust. And there was that dragon man that we've seen coming out of man. And I've seen a 3D print of the skull of that. It's huge. Oh, goodness. So there was that one. And there were, and in Eurasia came the Neanderthals. As the Ice Age got harder, the Neanderthals became more acclimatized to that way of life, and they spent a lot of their time underground and in caves. They didn't have big home ranges, so they cultivated an inner life. They built structures deep inside caves away from light, of possibly who knows what purpose. And then an offshoot of the Neanderthals went and lived in Tibet, the third pole of all these places. And I like to say they became the Yetis, the Denisovans. Yeah. Eventually they came back to lower levels, but they bequeathed to modern humans the gene that allows modern Tibetans to live at high altitude. That comes from the Denisovans. So all these creatures lived till at least 50,000 years ago. And by that time, modern humans were living in most of the world as well. Right. So modern humans would have encountered Neanderthals, Denisovans, all these little other creatures. I mean, 5 or 6 or more different species of human. Yeah. But after 50,000, Homo sapiens was the only one left. Yeah. By all sorts of strange chances. I mean, Homo sapiens nearly went extinct at least once.
It's so strange to think about it now, just because of all the things we know about evolution and humans, but it really is kind of remarkable. And obviously we know now that, humans are, basically just kind of engulfed and collided with Neanderthal DNA. And so that's kind of what put them out. And so it's interesting how we are the only ones that are left. And we're obviously very, we have populated the earth excessively, but, it's interesting to think that there were 6 or 7 and we were the ones that kind of made it out.
But the thing about modern humans is we're rather a raw ingredient. I mean, modern humans we've each got a little dusting of all these other hominins in us. I mean, any lineage that isn't purely African has 2 to 4% Neanderthal DNA. Right. And a lot of people in Southeast Asia have quite a lot of Denisovan DNA. Yeah. And of course, Neanderthal DNA as well. Right. And there are people in Africa who have DNA from hominins as yet unknown, only from the DNA. So there were a lot of hominins around. And so what seems to have happened is humans maybe have outcompeted them, but were certainly interbred with these other creatures. Yeah. And so human beings, in a strange way, preserve the heritage of a lot of these creatures.
Yeah, that's a nice way of putting it. So I guess getting here to the end, so we've really covered much of the story of Earth and much of how you tell it in your book. But towards the end, we're getting to the bonus materials, the extra billion years you give us. So how does humans' time on Earth end? Is it the AI, the robot overlords, climate change, and just what about life on Earth in general? When does it all, you think, kind of end?
Well, what I did in the book was I rather cheekily skipped over the most of human history and went straight to the future. I ended human history with a picture of young humans planting their handprints on a cave wall to say I am here. And then I skip over to talk about extinction and the future of life on Earth, and I say that humans won't last for another few thousand, tens of thousands of years. I've been thinking a lot about this lately, and it's quite a hard subject to understand. Will it be AI? Will it be the robot overlords? But purely in biological terms, mammal species tend not to last more than 1 million years because mammals tend to live fast and die young as species. But humans are exceptional, so because we're conscious of what we're doing. So in some ways we could, so it's very hard to predict what will happen with humans. We could all die out tomorrow, or we could be in here for millions of years. But I think the looking at the pure biology, I don't think we're destined to be here that long for a number of reasons. One is we're genetically, I mean, human beings look very variegated, but genetically we're all very, very similar indeed. I mean, there's more genetic variation in a few clans of chimpanzees than in the entire human species. And this is basically a relic of the fact that humans were almost completely wiped out and had to repopulate their Earth from a small number of people, relatively speaking. So there's that. And then there's a number of other things. One thing I don't explore, which I've started to think about, which is just recently the human sperm count has become disastrously low. That's true. Nobody really knows why. At least they might do, but please write in and tell me, because I haven't actually researched that yet. Another thing is, although the human population is huge and increasing, it's beginning to plateau out. And this is a consequence of a number of things. One is the general lack of resources. I mean, our generation is the first to have fewer resources than the baby boomers. There's less stuff to go around. But another thing, certainly in the short term, this is a huge benefit. Just in the last 100 years, and it's had the most seismic effect, and that's the emancipation of women all over the world. I mean, I'm talking broad brush here, more in some places than others. But as a result of that, people are living longer, and they're living much healthier, more fulfilled lives. More people are completing elementary education, and the workforce has doubled. And just a part of that is people are having fewer children than they did, because people don't have to keep breeding children to replace the ones that die of infectious diseases. I mean, of course, there are huge inequities, both in gender equality and in economic equality. But as a rule, things are getting more equal. Now, people are very short term, and they tend to think in very catastrophist ways. I'm a paleontologist, so I think in a very long term. I'm also a Brit, so I tend to think, come on, stiff upper lip, chaps. So, keep calm and carry on. It's not as bad as that. But although there's a great deal of hysteria about climate change and extinction, and a lot of it is entirely justified, it's not true that people aren't doing anything about it. And people have been doing things about it for quite a long time. There's this fantastic website called Our World in Data. Just dig into it, and it shows you some amazing things that made my hair stand on end. I mean, per capita energy consumption in the world is still going up, but it's actually going down in many developed countries. It peaked in the 1970s and plateaued and started going down. And when you think about all the little changes we've made that you don't really think about altogether, nobody drives these huge gas-guzzling cars anymore. Cars that you drive are much more energy efficient. And, we don't have all these devices anymore. We just have our iPhones. When I was a student, you used to go to a university with your entire record collection and a stereo system, and nobody does. My kids don't even know what a CD is. So, and all these tiny, tiny ways we're reducing our footprint. And it's not just recently, and people, and they're done in all sorts of small ways, driven by consumer choice as well as government. And the world population is still increasing. But the rate of increase peaked in 1968. it's now half that. It's in 1968 it was about 2 point something percent. Now it's 1 point something percent, and so we'll get to zero population growth sometime late in the century, in the 2060s, and then projections tend to vary after that about what will happen. But all of the projections show that around the end of the century, the population will be decreasing quite markedly, and the economic consequences of this are hard to imagine. I mean, who's going to pay for all the care of all these old people hanging around? I mean, that's a problem now in some countries like Japan. But there was a recent report in The Lancet. It was a report on the replacement rate of populations. Now, each woman has to have 2.1 children to keep the population at its present size. It should be 2 children, but they add the 0.1 because male children tend to die more than female children, and to factor in accidents and whatever. This is called the total replacement rate. It's now much less than that in many countries, even countries that you wouldn't imagine, what we would patronizingly call developing countries. The population is going down fast, and so much so that within a rather short time, some countries will have half their population that they do now. Not just Japan that everyone knows about, but Italy, Spain, Thailand, and countries like that. So it's so the population will shrink. Now, what happens to stabilize that, who knows? But I think with the combination of all these factors, I think and of course the rise of humans has been very rapid. The climate change that people have been causing, that really worrying, has only been since we started burning the coal from the Carboniferous period, maybe 200 years ago, which is hardly any time at all. It's hardly more than living memory. So the rise of carbon dioxide, which is marked and huge, it will be a very high peak, but very narrow, so that after that, humans will slowly decline and fizzle out for some reason or another. So that in 250 million years' time, we'd never know that we were here at all.
That's a crazy thing to think about. It's interesting to think about. Everyone thinks about death and dying, especially as we get older. It's interesting to think about our species not existing and our species, there not being any recollection or memory of our species, which is another terrifying thing to think about. But before we end here, I want to ask. I kind of want to end on a fun note. So I know you're a big fantasy fan, and you were a fan, I'm assuming, of Lord of the Rings and J.R.R. Tolkien, and I'm sure you've seen Game of Thrones and all that. So I guess my question here is aside from just the fun part about it, is do you think some of these, take for example Tolkien, who's obviously the greatest, right? He had no question there. Yeah, so he had all of his experiences in World War I, and you read Lord of the Rings and you definitely see it. But I guess he also was a linguist and he's brilliant and all these things. But his creation of Middle Earth, many people when they talk about fantasy writers, it's a lot of world building, right? Which is interesting. And how much do you think? I've read a biography on Tolkien a long time ago, and I can't recall at the moment, but how much do you think understanding of the Earth and, astronomy and geology and biology and many other humans, how much of that goes into making, either for Lord of the Rings or for just fantasy in general, more effective fantasy, or more, I don't want to say believable because that's kind of an oxymoron, but how much do you think our understanding of Earth or planets goes into making, when you're talking about world building in terms of a fantasy novel?
Well, I mean, that's quite interesting because Tolkien was not a natural scientist at all. I mean, he was very widely read. He started his creation purely linguistically. Because he was a linguist, there was no space in his life for music. He didn't, he wasn't interested in music. It was the sound of language that was the musical to him, and he was one of these gifted linguists who could pick up a language, in nothing flat. And also, he loved to reconstruct old languages. And he had this idea. His experience came out of the First World War. The biography you would have read was basically by Humphrey Carpenter, which was written in the 70s. But there's a much more recent one by John Garth called Tolkien and the Great War, because Tolkien's character was formed as during his time. He was on the Battle of the Somme. Right. And he was with his three friends, like the four hobbits, and two of his best friends died in the conflict, and the fourth one he got kind of estranged from in the early age. And in one of his critical analyses of Tolkien, Professor Tom Shippey says that Tolkien came from generations of writers who came out of war, whose only way of processing their experiences was through fantasy. And you can think of Mervyn Peake and Gormenghast. You can think of Olaf Stapledon and Starmaker. He was in the ambulance service in the First World War. And, the most famous one, Kurt Vonnegut and Slaughterhouse-Five. He lived through the bombing of Dresden. So he wrote Slaughterhouse-Five, this crazy, entertaining novel. So Shippey puts Tolkien as one of these. So Tolkien, when he was invalided out of the war, went back was in hospital and started to write a book called The Book of Lost Tales. And in the book, he writes a story called The Fall of Gondolin. And it's the fall of this beautiful elvish city to the powers of darkness by betrayal. And amazingly, he has dragons, but they're not dragons they later became. They were articulated iron fire-breathing monsters. They were machines. And this could only come from somebody who was raised in the spirit of chivalry and hand-to-hand combat, where it's brutal, but at least it's honest, who then witnessed tank battles and death by howitzers when somebody presses a button miles away and this enormous shell the size of a car comes and hits you. So that was his experience, but he also developed the elves as a kind of repository of these languages that he invented. He invented these languages and then he had to have somewhere to speak them. And when he had the speakers, he had to have the geography to put them in. But one of the interesting things to me as a paleontologist about Tolkien's world, and I wrote about this in a book called The Science of Middle-earth, was back in the days of Middle-earth, which is supposed to be in the fantasy and some bygone episode of the real world, there were all these different kinds of speaking human-type people that were all different, but all had their own languages and traditions. Of the elves and the dwarves and the ents and the orcs and all sorts of other people. And now there's only humans left. Tolkien has a bit in The Lord of the Rings after the great battle at Minas Tirith at the end. This is a bit that isn't in the film, it's in the book, where Legolas the elf and Gimli the dwarf are looking at the gates of Minas Tirith, which had been blasted off, and they say, we're going to build better gates. But they both reflect on the fact that the elves and the dwarfs, will soon be gone, and it'll be an age purely of humans. And that elves and dwarves will only be seen as bottom of the garden sprites and fairies to human beings that would come afterwards, rather than these powerful, very fully realized beings. And Tolkien wouldn't have known of the paleontology of today and the multiplicity of human beings that lived on the earth till recently. But that's something that strikes a chord with me, thinking about Tolkien. He was a great reader of science fiction. He was very fond of Asimov. His great friend C.S. Lewis. His great friend C.S. Lewis used to import pulp science fiction from the States. Gernsback's astounding science fiction, and so he was raised on the pulps. So this is something I kind of wheedled out of various writings. He could only have been learned of certain things from the pulp science fiction, but the world building. Tolkien was very skeptical about influence spotting. People would ask him, where he got certain ideas from, and he'd say, I don't know, they must have been composting in my head, and suddenly I wrote about them. The Ents were another.
Mm-hmm.
He said, where did the Ents come from? And he said, well, they must have come from the sort of compost of my mind. He loved trees. But Star Maker by Olaf Stapledon has walking trees, and there are all, he must have picked them up from all sorts of other places.
Mm-hmm.
That's my take on Tolkien.
Yeah, I mean, again, he's the best. I absolutely love him, and Lord of the Rings is, fantastic. But I like all of the other types of ancillary works as well. I guess a question about that is that George R.R. Martin with Game of Thrones is highly influenced by Tolkien. I don't know if he's admitted that publicly. Maybe he has. But I know it was very popular for a couple of years, the books of sorts, and then definitely the television show, and it's very well produced. But I'm quite critical of Game of Thrones. Do tell me what your thoughts are. Mine aren't really fully realised. I mean, I've discussed it with my daughter, who's a Game of Thrones fan. Yeah, so here I'm going to make half my listeners not listen to me anymore. So
I'll be the other half, and I'll still listen.
Look, I mean, I read Game of Thrones when it came out, the first couple books, and I thought they were good for the most part. Look, I read long form stuff all the time. I like long form pretty much everything, but there are things that the way he tells a story is, there could be some editing, right? I think the problem with Martin is that he becomes very fascinated with world building and does not take the time to have a central story of sorts. I mean, there's the idea of, okay, there's a kingdom, there's thrones, everyone's trying to get to the main throne. Okay, fine. But there's, you'll read about a character, and this is how the show is as well, for at least the first 5 seasons. You'll read about a character and maybe a couple characters, and then you won't hear about them for 60 pages. That's just a terrible way to write a story. The reason why Lord of the Rings works is it gives you everything you want, right? You have Middle Earth, you have elves, orcs, ents, dwarves, all these characters. You have all these subplots, wizards, the world of men. You have all of these places in Middle Earth. But the easy part about Lord of the Rings and why it works and why it won 12 Academy Awards or whatever it was that at the end of the day, it's a very easy story. There's a ring that we have to destroy in this place, and that's the journey. And there's 4 hobbits, 5 hobbits really, 5 hobbits and a couple of ancillary characters, and that's just the through line. And so the story is very consistent. The central cast of characters are pretty consistent, and then you can get all the other stuff if you want, but if you want to talk about Rohan, and if you want to talk about all the different types of places in Middle Earth, you can do that if you like, but you're not reading about Frodo and Sam and then Gollum later, and then you don't hear about them for 80 pages, right? Or in some cases with Game of Thrones, I guess it was kind of experimental, but you have basically book 4 and book 5, completely just one half of your characters in one story and another half in another book. So that's the thing with the books. I think it needs to be edited. I think he got lost in world building. It's not very it's kind of directionless in some ways. I don't think his characters are really, they're not, some of them are fine, but I mean, look, I think villains are always, fascinating creatures or like characters, but, and it is hard to write a good hero character. But I think Jon Snow is just absolutely pathetic, and it's just a terrible character. It's just a terrible character. It's just not. You look at Jon Snow and you look at Aragorn, and I am now comparing, but
you know nothing, Jon Snow.
Aragorn is a fantastic hero. He's a fantastic hero story, right? Yeah. Jon Snow is a 2-bit cartoon version of Aragorn, right? It's just and there's a lot of also obvious ripoffs in Game of Thrones. I mean, everyone's influenced by Tolkien if you're doing fantasy, but it's completely obvious. You know, in the Return of the King, where he has to get all of the kings from the Dead Valley, and they come and they fight and all that stuff. I mean, this is literally the White Walkers Redux. You know, it's just so like patently obvious, and it's not original. And I don't know. I could go on and on and on, but these are some of my main criticisms.
I think it's like the Game of Thrones. I read the first book and I didn't like it much. I thought it was very derivative and overwritten. But I've got the first book because I felt I had to read it. And, my daughter got me into it and I enjoyed it, but it was kind of a soap opera. Yes. I mean, there was one damn thing after another and things would happen. And I know what you mean. There are character arcs in there. Mm-hmm. My favorite character is Tyrion Lannister, is Peter Dinklage's character. By far, he makes it. And some of the scenes they did, the best ones were the small scenes. My favorite one is when Peter Dinklage is waiting in one of these castles for Daenerys to come back from wherever she's gone, and she's staying there with one of the Unsullied, the guy, Grey Worm, and I don't know, Melisande or whatever her name is, the interpreter, and they're just waiting. So he just gets them to tell a joke. I mean, it's this tiny scene, and that was my favourite. That's the one that's I don't know if Martin wrote that because I never got that far. And I thought it was okay, but I do know what you mean. But the thing is, The Lord of the Rings didn't start as a story like that. It started as one damn thing after another. And we now have the benefit of all the unpublished drafts of The Lord of the Rings, which have been published. I mean, you know, when I talked about writing my book, not that I would compare it with The Lord of the Rings, I mean, it became very simple, but it had a very complicated genesis. It was the same with The Lord of the Rings. He wrote The Hobbit as a children's story. Right. And it got published almost by accident. And it was a Christmas hit in 1937, the same year as Snow White and the Seven Dwarfs, one of the best films ever made, in my view. And his publisher said, "We want you to write another one." And he said, "I don't want to write anything more about hobbits. I'm more interested in elves and the Grand Silmarillion." So he started to write a story about Bilbo's heir called Ringo or Bungo or something, who has to go, and he's run out of all the treasure and he has to go and find some more. And the first few runs of The Lord of the Rings, he wrote a few chapters, gave up in disgust, but he never threw anything away. So all of the papers are still there. He started again from the beginning, wrote a few more chapters, gave up in disgust. And he started 5 times until he got to Rivendell. And then he realized he had a story. It was all to do with the ring that was picked up in Gollum's cave. And then we had a story. And this is one of the reasons why you have in the Fellowship of the Ring, not the film compresses that very well. They have all these digressions. They go and meet this character, Tom Bombadil, who comes out of nowhere, and then they say goodbye to him. I mean, what? What's that all about? So Peter Jackson very cleverly got rid of that. First rule of making a movie, prune out all the unnecessary characters. And, Tom Shippey wrote, they stop at least 5 homely houses before they even get to Rivendell. So it was only when he kind of rewrote the whole thing backwards that the actual story happened. And he used to write his son, Christopher, who then became the literary executor in later life. He was then in the RAF in South Africa. He wrote it during World War II, largely. And he used to write the story on these little airmail letters to Christopher in South Africa, and who would send his criticism back. But it grew very painfully over an awfully long time. And so the publisher, who wanted a nice, light children's story to immediately replace The Hobbit, 17 years later, got this immense pile of stuff. And, nowadays we have fantasy trilogies. They always happen to be trilogies. Well, the only reason was because the only way to publish this stuff was in 3 parts. Right. Because this was in 1954. In Britain, there was still paper rationing, and nobody would have been able to afford to buy it if it were more. And so basically they printed it and it bombed. And it only picked up when the counterculture got going. And the hippies. And Tolkien, this aged, very straight-laced professor, used to get phoned up at home by these strange characters from California, and which he found very distressing. So the Lord of the Rings kind of happened by accident. He wasn't really interested in that. He was interested in the Silmarillion. He wanted to publish that, and no one was interested.
Yeah, no, I mean, I agree with you. And look, if you take Lord of the Rings by itself, even in the final product, it's dry reading. Like, it's not like it's kind of dry. Well, that's fine. I guess with Game of Thrones is that I mean, the damn thing's still not finished, and I just don't think the characters are that good. Look. My favorite character in Game of Thrones is Cersei, because
she's quite a strange character.
Very dynamic. She's got a lot going on internally.
Yeah,
she is absolutely fascinating, and she was my favorite on the show. But I mean, you haven't read all the books, but and they're not finished. But Tyrion was fine, but then I just the last 2 seasons of the show, I was really bored with it.
You see, I'm going to be very unpopular. I actually quite like the way it finished.
I like the ending too. Everyone was upset about the ending.
Yeah, why?
I was fine with it.
Basically, it kind of puts together the character arc. That basically, rather than being one thing after another, it was the story of the Starks. It was the story because it began with Ned Stark, and then he was killed off at the end of the first series. Marks at everyone's shot, because you don't do that with characters. But then that was one of the good things about Game of Thrones. It would suddenly throw you a curveball where, you get the Red Wedding where everybody would be wiped out. You think, oh, what's going to happen now? But at the end, all the Starks, after these long digressions, there's Brandon and the Three-Eyed Raven and the Arya. I liked Arya Stark's business with the faceless people and what. The young queen,
Sansa.
So, she starts off as being this silly girly.
Yeah, her arc is very good. Her arc is very good.
With fantasies of being a princess in a castle, and then she goes through this cruel, awful set of experiences, and becomes very hard.
Yes,
hard at the end. So I think the series wound it up, but it was. Oh boy, it was too long, and there were too many people in it. And you do get the impression that for a long time it was just coasting.
It was very bloated and just it was kind of directionless.
But you could say the bit about a lot of the Lord of the Rings. I mean, they didn't dare edit Tolkien because he would take it very personally. He'd go back and rewrite the whole thing, and you wouldn't see it for another 10 years. Yeah. So they thought, oh, we got it. We'll do something now with it. So. Of course, these things are products of their time. I mean, any fantasy now can only have echoes of Tolkien in it. Sure. I mean, here's another thing that was immensely popular: the whole Harry Potter thing.
Yes.
I mean, what? How?
Yes.
I mean, I've read all of Harry Potter several times to my kids at bedtime, and it was very entertaining. But it's more full of holes than a colander. I mean, as a piece of world building, it's very poor. As a piece of writing, it's very poor. I can't understand. It seems to have just caught the mood of children at a certain time, and it spread by word of mouth. I think it's because J.K. Rowling did what all good children's authors do, in is they do not talk down to their audience.
Yeah.
And I know this because I had basically a control experiment. I remember we'd moved house at one point, and I think we had one very small child and the other wasn't quite on the way. And we moved house, and I was up in the back bedroom painting the ceiling, and I had the radio on. And in Britain, there's this radio program called Book Club, where an author is quizzed about their book by an audience of readers with a kind of master of ceremonies. And I switched on halfway through, and there was this group of 11-year-olds talking to this lady author about characters called Hermione and Harry, and I didn't know what this was about. I had no idea. And J.K. Rowling was talking to them as if they were grown-ups. He wasn't patronising at all.
Yes.
But I didn't know who she was. I had no idea. So I went downstairs at lunchtime and I said to my wife, "What's all this?" And she said, "Haven't you heard about Harry Potter? It's the latest literary sensation. I think the second book was about to come out." But, I think books for children mustn't take any prisoners. I don't know about The Hobbit. That was written in a kind of slightly patronising way. But when you think about my favourite... Narnia, my favourite children's book. It's very short. It's written for very young children. But it's all about a struggling one-parent family, a mother who's trying to support 4 children on nothing by selling things in the street. Her son is a juvenile delinquent and goes off the rails. And their father was a career burglar who was killed by one of the people he was burgling. The story is Peter Rabbit. She takes no prisoners. Don't go into Mr. McGregor's garden. Your father had an accident there. He was put in a pie by Mrs. McGregor. I loved that when I was 3. But so with Harry Potter, they didn't take any prisoners, and they go through some tough stuff.
Yeah,
but maybe it's the kids identified with the characters rather than the fact that the story was any good.
I totally agree with you about how she doesn't talk down to children. She treats them as basically little people, right?
Well, she respects them as readers.
Yeah, absolutely. And I think kids really got that. And again, this is right before, the internet really took off. And so, she kind of caught that last wave. But then also, I agree, there's plot holes. The world building's not that great, but it was a very simple story. It's got some really cool symbolism. It's got a central cast of characters. Okay. Yeah. But it also it has the really good imagination piece of it. But what it did was it really gave a structure and organized the world of wizards. And we had never really had anything like that in that way with all of those types of things. It's not very original, right? This a boy has special powers, or there's something, but I agree with you about the world building, but I do think that we have something so grand with the world of magic and wizards, and it's a school, and there's nothing really like that. And so I think if you take that plus how she doesn't talk down to the kids.
I think it was the mixture of all the things together. Yeah. But but also it did build on certain archetypes.
Yes.
She in this program, she identified with Hermione. She was she was the SWAT. She was the girl at school who was the nerd. But then Harry is the boy with special powers who comes from the wrong side of the tracks, and and then but there's Albus Dumbledore. Albus Gandalf Obi-Wan Kenobi Dumbledore. It's the mage, the mentor, which you have to have, but. I asked my daughter about Game of Thrones, and she says that she'd read somewhere that it was basically modelled on the War of the Roses, which was a Game of Thrones and incredibly complicated with all these shifting alliances. So maybe that explains why it's so complicated. Yeah,
it could. I mean, it very well could. I will read whenever it's supposed to be 2 books left. I will read it. So when it finishes, but we'll see. Yeah. Well, look. Henry, you have been super, super, super generous with your time and your energy.
Oh, it's been so much fun. It's so much fun.
Absolute blast. I really have enjoyed it.
It's what my son calls a good old chat.
Yes, absolutely. And that's what it was. The book is A Very Short History of Life on Earth, 4.6 billion years in 12 pithy chapters. It is out in November. And where can people buy it, and where can people find you online and your work?
Well, it's out on November 9th, and it's in the proverbial all good bookstores. And I've got a website for it called A Very Short History of Life on Earth.com. And that's where I put all the news. And on that page, you can find me on Facebook and Instagram and Twitter and LinkedIn, but I'm too old for TikTok. And that's where you can find me.
No, that's great, Henry. It was more than a blast. It's a big honor. I really just had so much fun talking to you about all this stuff.
Yeah,
I
likewise.
really appreciate it.
Likewise. Thanks for asking me. It's been so much fun.
Absolutely. Thank you.